Have you ever tried to hold infinity in the palm of your hand? It sounds like a riddle, or perhaps a line from a poem you might read before drifting off to sleep, but it is actually one of the most profound physical questions we can ask about the universe we live in. When we think of infinity, our minds instinctively cast their gaze outward toward the horizon that never ends, or upward into the crushing depth of the night sky, where stars are scattered like diamond dust across a canvas of velvet darkness. We imagine infinity as a distance, a journey that goes on forever, past the moon, past the rings of Saturn, past the icy silence of the Kuiper Belt, and out into the intergalactic void, where galaxies float like islands in a sea of nothingness. We think of it as out there, a concept so vast that it belongs only to the giants of cosmology, to the black holes and the expanding edges of the observable universe. But what if I told you that you are looking in the wrong direction? What if I told you that the most mind-bending, paradoxical, and terrifying version of infinity is not billions of light years away, but right here, sitting quietly between the tip of your finger and the screen you're looking at? If you bring your hand close to your face and really look at it, you see skin, texture, lines that map the history of your movements. It looks solid. It feels complete. But physics tells us that this solidity is a magnificent illusion. If we could shrink ourselves down, peeling back the layers of reality like the petals of a cosmic flower, we would find that the space you occupy is almost entirely empty. You are made of atoms, and atoms are confusingly spacious cathedrals. If the nucleus of an atom were the size of a marble sitting on the center line of a football stadium, the electrons would be tiny specks buzzing in the highest nosebleed seats, and everything in between, that vast, silent field, would be empty space. We are, in a very literal sense, ghosts haunting a shell of electromagnetism. But this emptiness poses a dangerous question. If there is space between the parts of you, can we divide that space? And if we divide it, is there space between the divisions? Before we descend further into this microscopic abyss to find what infinity is truly made of, I want to welcome you to this quiet corner of the internet. I am Walter, the Explorer, and my goal is to guide you through the strangest mysteries of the cosmos while helping you find a moment of peace in your day. I notice that about 73% of you traveling with me right now have not yet subscribed to the channel. If you enjoy these journeys into the unknown, please consider subscribing. It truly helps us keep exploring the universe together. Now, let us return to the space between your fingers. To understand the problem of infinity, we have to go back to a dusty road in ancient Greece, where a philosopher named Zeno proposed a paradox that has kept scientists awake for 2,500 years. Zeno argued that motion is impossible. He said that to get from point A to point B, you first have to travel half the distance. But before you can travel half, you must travel a quarter. And before a quarter, an eighth. You can keep dividing the distance forever. 1/2, 1/4, 1/8, 1/16. The fractions get smaller, but they never reach zero. Zeno argued that because space is infinitely divisible, you would have to complete an infinite number of tasks just to move your finger a single inch. In a world where space is smooth and continuous, motion should be impossible. You should be frozen, trapped in a prison of infinite fractions. And yet, you can move, you can breathe, you can close your eyes. So, for centuries, we assumed Zeno was just playing a word game. We assumed that, yes, space is infinite, but we just glide over it. But then came the 20th century, and with it, the strange and beautiful revolution of quantum physics. When physicists began to look at the universe with the mathematical precision of the quantum realm, they found something that shattered the idea of smooth, continuous space. They found a wall, a limit, a pixel size for the universe. We call this the Planck length. It is a distance so small that it makes an atom look like a galaxy. To be precise, the Planck length is approximately 1.6 times 10 to the power of negative 35 meters. Let us try to visualize that number, because our brains are not built for such scales. If you were to take a single dot at the end of a sentence and magnify it until it was the size of the entire observable universe, spanning 93 billion light years, a single Planck length inside that dot would still be only about the size of a single tree. That is how small the fabric of reality is. This discovery suggests something profound and slightly unsettling. The universe is not smooth. It is not a continuous sheet of silk. It is more like a digital photograph made of tiny, discrete chunks. There is a here and a there, but nothing in between. When an electron moves, it does not slide through the space between Planck lengths. It simply vanishes from one location and appears in another, teleporting through the microfabric of the cosmos. This resolution to Zeno's paradox brings a certain kind of peace. It tells us that we can move because space is not infinite in the way we thought. It has a bottom. It has a grainy texture. We are living in a low-resolution simulation, but the pixels are just too small for us to see. However, just as we thought we had solved the riddle, quantum mechanics opened a door to a much deeper, darker room. If space is made of these tiny Planck-sized boxes, what is inside the boxes? You might think the answer is nothing. You might think that if you remove all the atoms, all the light, and all the radiation, you are left with a pure, empty void, a vacuum. A silence so absolute that it creates a perfect zero. But the universe does not allow for zero. One of the fundamental rules of the quantum world is the Heisenberg uncertainty principle. It tells us that we can never know everything about a particle at once. We cannot know its position and its momentum with perfect accuracy. If we try to pin down a particle's location, its speed becomes wild and uncertain. But here is the catch. This rule applies to empty space, too. If we say a box of vacuum has zero energy, we are being too precise. We are saying we know exactly what the energy is, zero, and exactly where it is. The universe forbids this. It demands uncertainty. It demands a jitter. So, even in the deepest, darkest void, where absolutely nothing should exist, the laws of physics force the empty space to boil. Virtual particles pop into existence and annihilate each other in timescales so short they barely register as real. They borrow energy from the future and pay it back in the past. This is not just a theory. We have measured it. We have seen the effects of this quantum foam pushing metal plates together in the Casimir effect. We know the void is alive. But this leads us to the greatest embarrassment in the history of physics, a paradox that makes Zeno's riddle look like child's play. When physicists tried to calculate how much energy is inside this empty space, how much power is contained in the infinite jitter of the quantum vacuum, they came up with a number. They calculated that the energy density of the vacuum, the weight of nothingness, should be roughly 10 to the power of 113 joules per cubic meter. That number is a 1 followed by 113 zeros. It is a number so large that if it were true, the space inside your empty coffee cup would contain enough energy to boil all the oceans on Earth instantly. In fact, it would contain enough mass to collapse the entire universe into a black hole the size of a subatomic particle. But look around you. The universe has not collapsed. You are not being crushed by the weight of the empty air in front of you. The stars are drifting gently, not being ripped apart by a vacuum loaded with infinite power. When astronomers look at how the universe is actually expanding, they measure the energy of empty space to be incredibly small, almost zero. The difference between the theoretical infinity of quantum energy and the gentle reality we observe is a factor of 10 to the power of 120. This is the vacuum catastrophe. It is the biggest wrong answer humans have ever calculated. So we are left with a beautiful, terrifying mystery. According to our best equations, the infinity inside the microscopic world is made of a raging storm of energy, a fire that burns in every millimeter of existence. Yet, according to our eyes and our telescopes, the universe is quiet, spacious, and stable. Where did all that energy go? Is it hidden? Is it canceled out by some perfect cosmic symmetry we have not yet discovered? Or is our understanding of infinity fundamentally broken? As you lay there, perhaps feeling the weight of the blanket on your body or the stillness of the room, consider this. You are floating on an ocean of infinite potential. The silence around you is not empty. It is full. The very fabric of reality that holds you is vibrating with a power we cannot comprehend. And yet, somehow, it balances out to let you exist in peace. We are walking on a tightrope over an infinite abyss of energy, but the rope is steady. The universe holds us. In the next chapter, we will try to understand what happens when we try to break this limit. We will journey into the heart of a black hole, where the laws of the Planck length clash with the crushing force of gravity, and where the concept of infinity stops being a mathematical game and becomes a monster that eats light. We will ask, if space is pixelated, what happens when you squeeze too much information into one pixel? Does the universe crash? For now, just breathe. Feel the air entering your lungs, occupying the space inside you. Remember that even the empty space is dancing. You are never truly alone, for the void itself is alive with the heartbeat of the quantum world. We began our journey by looking at the palm of your hand, discovering that the solidity you feel is an illusion, masking a universe of empty space and vibrating energy. We found that if you zoom in deep enough, past the cells, past the atoms, past the electrons, you hit a wall, the Planck length, the pixel size of reality. We learned that space is not a smooth, infinite slide, but a granular staircase where the universe takes tiny, discrete steps. But now, I want you to close your eyes and imagine the opposite of that empty space. Imagine taking all the air in your room, all the furniture, the building you're in, the city, the planet Earth, the sun, and the billions of stars in our galaxy, and crushing them. Imagine a force so relentless, so overpowering, that it refuses to stop squeezing. This force is gravity, the silent architect of the cosmos. And when gravity wins its ultimate battle against matter, it creates the most paradoxical object in existence, a black hole. To understand why black holes break our understanding of infinity, we have to look at what happens when a massive star dies. For millions of years, a star is a delicate balance, a wrestling match between two titans. Pushing out is the explosive energy of nuclear fusion, the fire that makes the star shine. Pushing in is gravity, trying to collapse the star under its own weight. As long as the fuel burns, the star holds itself up, but eventually the fuel runs out, the fire dies, and gravity, which never sleeps and never tires, takes over instantly. In a fraction of a second, the core of the star collapses. If the star is massive enough, say 20 times the mass of our sun, that collapse does not stop at a neutron star. It does not stop at a white dwarf. It keeps going. It crushes atoms until electrons are shoved into protons. It crushes neutrons until they overlap. It squeezes matter into a space smaller than a city, then smaller than a house, then smaller than an atom. According to Albert Einstein and his beautiful theory of general relativity, this collapse should continue until the star occupies zero volume. It should become a point of infinite density. This is what we call a singularity, and this is where the universe, as we understand it, begins to scream. You see, a singularity is a mathematical infinity. It is a divide by zero error in the code of reality. It suggests that you can have a limitless amount of mass in a space that has no size at all. But remember what we found in the last chapter? We found the Planck length. We found that the universe has a minimum pixel size. Quantum mechanics screams that you cannot have a point smaller than a Planck length. You cannot squeeze information into a space that does not exist. So, here we have the two greatest theories of physics: general relativity, the master of the large, and quantum mechanics, the master of the small, locked in a fistfight at the center of a black hole. Einstein says, the space is smooth, curve it infinitely. Quantum mechanics says, the space is pixelated, you cannot go smaller than 1 pixel. Who is right? What actually happens at the center of a black hole? This is the greatest mystery in modern physics, and the answer might redefine what infinity actually means. Let us drift closer to this monster to see the problem for ourselves. Imagine you are floating in the safety of a spaceship approaching a black hole. From a distance, it looks like a hole in the fabric of the night, a sphere of absolute nothingness surrounded by a ring of bent, twisted starlight. This ring is the accretion disk, matter that is spiraling in at nearly the speed of light, glowing with the heat of friction. But the black sphere itself is the event horizon. This is the point of no return. It is the silence at the end of the universe. The event horizon is not a solid surface. You could fly right through it without hitting anything. It is simply a boundary in space where the pull of gravity becomes faster than the speed of light. Since light is the fastest carrier of information in the universe, nothing that happens inside this boundary can ever send a message to the outside. It is a cosmic censorship. But strange things happen to time here. If I stayed on the ship and watched you fall toward the horizon, I would never see you cross it. As you get closer to the incredible gravity, the light coming from your body would struggle to climb out of the gravity well. It would lose energy, stretching into longer, redder wavelengths. I would see your movements slow down. Your wave would become a slow-motion gesture that takes years to complete. To me, you would appear to freeze just above the edge, fading slowly into redness and silence, hanging there for all of eternity, never truly entering the dark. But to you, falling in, the experience would be terrifyingly different. You would cross the horizon in a normal amount of time. You would look back and see the universe outside still shining. But you could never go back. Gravity would seize you, pulling your feet harder than your head, stretching you into a long, thin strand of atoms in a process physicists actually call spaghettification. But let us assume for a moment that you could survive this. Let us assume you could fall all the way to the center, to the singularity. What would you find? If general relativity is right, you would find the end of time. In Einstein's math, space and time switch roles inside a black hole. The direction down towards the center becomes a direction in time. You can no more avoid hitting the singularity than you can avoid next Tuesday. It is in your future, and when you hit it, you hit the end of the timeline. The infinity of density crushes existence into a stop. But if quantum mechanics is right, something else must happen. Some physicists propose that the pixel structure of space prevents the singularity from ever forming. Instead of an infinite point, the collapsing star might stop when it reaches the density of the Planck length. It might form a Planck star, a dense, vibrating core of quantum space-time that is holding its breath, waiting to exhale. Because time is so warped, this core might be bouncing back, exploding outward, but the extreme gravity slows that explosion down so much that to us, on the outside, it looks like a static black hole that lasts for billions of years. In this view, a black hole is not a grave. It is a star in the middle of a very, very slow explosion. This brings us to the problem of information. In our universe, one of the most sacred rules is that information is never lost. If you burn a book, the information in it is not destroyed. It is scrambled. If you could collect every photon of light, every particle of ash, and every molecule of smoke, you could, in theory, reconstruct the book. The universe keeps a record of everything. But if a black hole crushes matter into a singularity, and that singularity disappears, or is cut off from the universe, where does the information go? Does the universe forget? In the 1970s, Stephen Hawking and Jacob Bekenstein made a discovery that changed everything. They realized that the size of a black hole's memory, the amount of information it can hold, is not determined by its volume, as you might expect. If you fill a library with books, the number of books depends on the volume of the room. But for a black hole, the information seems to be stored on the surface area of the event horizon. Think about that. The inside does not matter. The record of everything that has ever fallen in, every star, every planet, every photon of light, is plastered on the two-dimensional shell of the horizon, like stickers on a suitcase. This suggests that the infinity inside a black hole might be an illusion. The three-dimensional depth we perceive, the sensation of falling in, might be a hologram. The reality might be a two-dimensional surface full of data, and the third dimension, the space inside, is just a projection of that data. This is called the holographic principle. It implies that at the deepest level, the universe, and perhaps you and I, are just information painted on a distant surface, projected into the solidity we feel. So, we return to the pixel. The event horizon is covered in tiny Planck-sized squares, each one holding a single bit of information, a 1 or a 0. The black hole is not an infinite pit. It is a hard drive. It has a storage limit. It can only hold as much information as its surface area allows. If you try to throw one more bit of information in, the black hole has to grow. The horizon has to expand to make room for that one new pixel of data. This is the physical proof that infinity has a limit. You cannot pack infinite information into a finite space. The universe counts its bits. There is a strange comfort in this. It means that chaos is not allowed to win completely. Even in the most violent place in the cosmos, where gravity shreds stars and eats light, there is an order. There is a ledger. The universe is writing down everything that happens. Nothing is truly forgotten. The ghosts of the stars that fell in are still there, encoded on the silent, dark sphere of the horizon, whispering their story in the language of quantum geometry. As we drift away from the event horizon, pulling back from the brink of the abyss, let the heaviness of this concept settle. The gravity that holds you to your bed is the same force that, when multiplied, challenges the very logic of reality. It tries to create infinity, but the quantum pixels of the universe stand firm, holding up a hand and saying, "Stop. Here is the limit." You are living in a universe that has boundaries, rules, and a fundamental structure that protects us from the chaos of the infinite. But if the black hole is a hard drive, and if information is stored on the surface, what happens when the black hole dies? Because black holes do not live forever. They evaporate. They bleed energy into the cold void. And if they disappear, what happens to the library of information stored on their skin? Does the book of the universe get deleted? This is the information paradox, and it is the cliffhanger at the end of modern physics. In the next chapter, we will leave the dark gravity of the black hole and travel to the opposite end of the spectrum. We will look at light. We will ask how a photon, a particle with no mass, can travel for billions of years without getting tired. We will explore the speed of light, not as a speed, but as another kind of prison, a limit that locks us in a cage of causality. We will ask, if time stops at the speed of light, does a photon experience the universe at all? Or does it exist everywhere at once? For now, release the tension of the singularity. Let your mind expand back out from the microscopic pixel, back out from the crushing gravity to the quiet room you are in. Feel the stability of the floor. Feel the gentle passage of time, ticking forward second by second, safely away from the event horizon. You are here. You are safe. And the universe is still writing your story, one plank length at a time. We ended our last journey at the edge of a black hole, staring into the face of a gravity so strong it breaks the concept of geometry, turning the universe into a hard drive of frozen information. We learned that space has a limit, a pixel size, and that even the darkest pits of the cosmos have a memory. But now, I want you to turn away from the dark. I want you to imagine a single, solitary particle of light. A photon. It is the messenger of the universe, the carrier of everything you have ever seen, every color you have ever admired, and every star you have ever wished upon. It seems fragile, a tiny packet of energy that can be stopped by a piece of paper or absorbed by a leaf to make sugar. But this fragility is a mask. The photon is the ruler of the cosmos. It dictates the speed at which reality happens. And if we look closely at its journey, we find that light, the very thing that allows us to see the universe, might be the most lonely and paradoxical thing in it. To understand the infinity of light, we have to talk about speed. In our human lives, speed is something we feel. We feel the wind on our faces when we run. We feel the press of the seat against our backs in a fast car. We think of speed as something that can always increase. If you are going 60 miles per hour, you can go 70. If you build a better engine, you can go 100. In our intuition, speed is infinite. You can always add 1 more mile per hour. But the universe disagrees. The universe has a speed limit, and it is absolute. We call it the speed of light, denoted by the letter c. It is exactly 299,792,458 meters per second. Why this specific number? Why not 300 million? Why not infinity? Physics tells us that this number is not just about light. It is the speed of causality. It is the maximum speed at which one event in the universe can affect another event. If the sun were to suddenly vanish right now, gravity would not stop holding us instantly. The Earth would continue to orbit the empty space where the sun used to be for 8 minutes and 20 seconds. We would still see the sun shining in the sky. We would still feel its warmth. For 8 minutes, we would be living in a ghost solar system orbiting a memory. The news of the sun's death has to travel across the vacuum, and it can only travel at c. This speed limit keeps the universe from happening all at once. It separates cause from effect. Without it, everything would happen simultaneously, and history would be impossible. But here is where the story gets strange. Albert Einstein, in his special theory of relativity, taught us that space and time are not separate things. They are woven together into a fabric called space-time. And he discovered a rule that feels like magic. The faster you move through space, the slower you move through time. You are always traveling through space-time at a constant speed. Right now, sitting still, you're traveling entirely through time. You're moving toward tomorrow at a steady pace. But if you get in a rocket and move through space, you have to divert some of your speed from time to space. Your watch ticks slower. Your heart beats slower. If you could travel at 99% of the speed of light, you could fly to the nearest star and back in what felt like a few weeks, only to find that on Earth years had passed. Everyone you knew would be older, while you remained young. You would have traveled into the future. Now, take this to its limit. What happens if you travel at 100% of the speed of light? If you use all your motion to move through space, you have none left for time. Time stops. For a photon, the clock is frozen. This means that, from the perspective of a particle of light, it does not experience time. It does not experience distance. When a photon is born in the heart of a distant galaxy, say IC 1101, which lies over 1 billion light-years away, and it travels across the intergalactic void to land on the mirror of the Hubble Space Telescope, we say that journey took 1 billion years. We see the galaxy as it was 1 billion years ago. We see ancient history. But for the photon, the moment it was emitted by the star and the moment it hit the telescope were the same moment. It did not feel 1 billion years pass. It did not see the emptiness of the void. For the photon, the universe contracted to a single point. The emission and the absorption happened instantly. In its own frame of reference, light exists in an eternal now. It is everywhere along its path simultaneously. This is the paradox of light. It is the thing that defines time for us, yet it is timeless itself. It connects the beginning of the universe to the end in a single, instantaneous leap. So, when you look up at the night sky, you are not just looking at distant objects. You are looking at a tapestry of different times. You see the moon as it was 1 second ago. You see Jupiter as it was 40 minutes ago. You see the Andromeda Galaxy as it was 2.5 million years ago, when human ancestors were just learning to make tools. And if you look at a giant like IC 1101, you are seeing light that began its journey when life on Earth was nothing but slime in the ocean. The night sky is a time machine, and we are trapped in the center of it, unable to ever see the present of the universe. We are always, eternally, looking into the past. But there is a barrier here, a wall of infinity that we cannot climb. Because light has a finite speed, and the universe has a finite age, about 13.8 billion years, there is a horizon beyond which we cannot see. We call this the observable universe. It is a bubble around us, about 93 billion light years across. Why 93 billion if the universe is only 13 billion years old? Because space itself has expanded, stretching the distance. But the limit remains. Anything outside this bubble is lost to us. There are galaxies out there, stars, perhaps civilizations, but their light has not had enough time since the Big Bang to reach us. They are severed from our reality. And this brings us to the prison of causality. Because we cannot travel faster than light, we are locked in a cone of influence. We can only affect things that light can reach. If you wanted to visit the edge of the universe, you would need infinite energy. As you approach the speed of light, your mass increases. At 99%, you are heavy. At 99.9%, you are heavier. To reach 100%, you would become infinitely heavy, and you would need all the energy in the cosmos just to push you that last little bit. The universe forbids matter from reaching the speed of light because it refuses to let us have infinite energy. It puts up a wall. It says, you can go this fast and no faster. This limit protects us. If we could go faster than light, we could outrun our own signals. We could arrive before we left. We could send a message back in time to stop our own birth. We could break the logic of cause and effect that holds reality together. The speed of light is the bars of a cell that keeps the universe sane. It ensures that the past stays in the past and the future stays in the future. It prevents the chaos of time travel from unraveling the fabric of existence. But let us go deeper into the photon itself. We know it acts like a particle, a tiny bullet of light. But we also know it acts like a wave, a ripple in the electromagnetic field. This is the wave-particle duality, the heart of quantum mechanics. When you are not looking at a photon, it behaves like a wave. It spreads out. It takes every possible path to its destination. If you shine a light through two slits in a barrier, the photon goes through both slits at once. It interferes with itself. It exists in a superposition of possibilities. But the moment you measure it, the moment it hits your retina or a camera detector, it snaps into a single position. It becomes a particle. This suggests that the universe is only real when we interact with it. Before the photon hits your eye, it is just a probability, a cloud of maybe. It is a ghost. By looking at the star, you force the universe to make a decision. You force the light to be here and not there. In a strange way, the act of observation builds the reality around us. We are not just passive observers watching a show. We are active participants. Our eyes are collapsing the wave functions of the universe, turning the infinite possibilities of the quantum world into the finite reality of the present moment. Consider the journey of a photon created in the center of our sun. In the core, nuclear fusion crushes hydrogen into helium, releasing energy. A photon is born, but the core is so dense, so packed with protons and electrons, that the photon cannot travel in a straight line. It moves a tiny fraction of a centimeter and hits a proton. It bounces. It moves another tiny bit and hits an electron. It bounces again. It is trapped in a random walk, a drunkard's staggering path through the blinding crush of the stellar interior. It can take 100,000 years for that single photon to fight its way from the core to the surface of the sun. 100,000 years of bouncing, absorbed and re-emitted, losing energy, changing from a deadly gamma ray into visible light. And then, finally, It breaks free. It reaches the photosphere, the surface. The density drops. The path is clear. It leaps into the vacuum of space. After 100,000 years of struggle, it crosses the 93 million miles to Earth in just 8 minutes. It screams through the atmosphere, dodging air molecules, passes through the lens of your eye, and strikes your retina. And in that final moment, it dies. Its energy is absorbed by a neuron, becoming an electrical signal that your brain interprets as light. The photon gave its life to let you see. Its entire existence, from the ancient fusion in the core to the final impact in your eye, was a journey to deliver a single packet of information to you. This connection is intimate. The light touching you now is a physical messenger. But what happens to the light that misses Earth? What happens to the photons from IC 111 that travel for 1 billion years and pass right by us, heading out into the empty blackness of the intergalactic void? They keep going. They travel forever. Unless they hit something, they will never stop. They will carry the image of that galaxy for eternity, a message in a bottle floating in the dark ocean of space-time, waiting for an eye that may never open to see it. The universe is full of this wasted light. Trillions upon trillions of photons are streaming through every cubic meter of space, carrying images of stars, galaxies, nebulas, and perhaps alien worlds. We are bathing in a sea of information we cannot see. The air around you is filled with radio waves, Wi-Fi signals, cellular data, and the ancient radiation left over from the Big Bang itself. We are blind to almost all of it. Our eyes can only see a tiny sliver of the spectrum, a microscopic window into the infinite reality. But there is something even stranger happening to light as it travels through the expanding universe. We mentioned earlier that the universe is expanding, stretching the space between galaxies. When space stretches, it stretches the light traveling through it. A wave of blue light, which is short and energetic, gets pulled like a rubber band as it flies through expanding space. It becomes longer. It becomes redder. We call this redshift. The farther away a galaxy is, the redder it looks, because its light has been traveling through expanding space for longer. If we look far enough, the light gets stretched so much it stops being visible light. It becomes infrared, and then it becomes radio waves. This is how we know the universe had a beginning. When we look at the empty sky with radio telescopes, we see a faint glow coming from every direction. This is the cosmic microwave background. It is the afterglow of the Big Bang itself. It is the oldest light in the universe, stretched by 13.8 billion years of expansion until it is just a cold, weak hum. But it is there. The fire of the creation is still burning, cooled down by the expansion of infinity. This expansion leads us to a terrifying thought. If space keeps stretching, eventually the distant galaxies will be moving away from us faster than the speed of light. Their light will try to reach us, but the space will grow faster than the photon can travel. It is like running on a treadmill that is speeding up. Eventually, the light will fall off the back. Those galaxies will disappear from our sky. They will fade into the true, absolute black. Future civilizations, billions of years from now, might look up and see nothing but their own galaxy. They will think they are alone in a static, empty universe. The evidence of the Big Bang, the evidence of other galaxies, the evidence of the expansion, all of it will have been erased by the horizon of light. We are living in a privileged time. We are living in the era of the universe where the light can still reach us. We can still see the history of the cosmos. We can still see the neighbors. But the prison walls are expanding, and one day they will leave us in solitary confinement. As you lie there, let your mind rest on the speed of light. It is fast, yes, but it is also a protector. It keeps the past safe. It keeps the present orderly, and it connects you to the stars. The light hitting your eyes, or the light from your screen, is a stream of particles that have obeyed the strictest law in the cosmos just to reach you. You are the destination of a journey that started before you were born. But what is driving this expansion? What is the force that is stretching the light and pushing the galaxies away? If gravity tries to pull everything together, why is the universe flying apart? In the next chapter, we will confront the invisible giant that makes up 68% of the universe. We will talk about dark energy. We will ask if nothing has a force. We will explore the idea that the vacuum of space is not just boiling with quantum particles, but is actually pushing back, driving the cosmos toward a cold, lonely, infinite end. We will ask, is infinity growing? For now, close your eyes and imagine the photons bouncing around the room, tiny, timeless ghosts stitching your reality together, one interaction at a time. The universe is bright, and you are the witness it has been waiting for. In the silence of your room, everything feels still. The walls are solid, the air is calm, and the ground beneath you feels permanent. We are creatures of gravity, evolved to understand a world where things fall down, where heavy objects stay put, and where forces pull things together. When you drop a cup, it shatters on the floor. When you look at the solar system, planets orbit the sun. Gravity is the great connector, the cosmic hug that holds the universe in a tight, understandable embrace. For centuries, we believed that gravity was the ultimate destiny of everything. We thought that because all matter has mass, and all mass attracts all other mass, the expansion of the universe that began with the Big Bang would eventually slow down. We thought the cosmos was like a ball thrown into the air. It goes up, it slows down, and eventually it either stops or falls back down. We comforted ourselves with the idea that the universe was a cycle, or at least a story with a gentle, breaking finish. But in 1998, two teams of astronomers looked deep into the night sky, measuring the light of distant exploding stars called Type 1a supernovas. They were trying to measure how much the universe was slowing down. They were looking for the break of gravity. Instead, they found the accelerator. They discovered that the distant galaxies were not slowing down at all. They were speeding up. They were flying away from us faster than they had been in the past. The ball thrown into the air was not falling back down. It was sprouting rocket engines and shooting off into the void. This discovery broke physics. It meant that there was something else in the universe, something invisible, something that pushed instead of pulled. We called it dark energy, and it is not just a small curiosity. It makes up roughly 68% of the total energy in the cosmos. Think about that. All the stars, all the planets, all the gas, all the dust, all the black holes, and even you, all of that normal matter, is less than 5% of the universe. The rest is darkness. Dark energy is the dominant power in reality, and we do not know what it is. We know what it does, though. It acts as a kind of anti-gravity. But unlike gravity, which gets weaker as things get farther apart, dark energy seems to be a property of space itself. This is the terrifying part. As the universe expands, it creates more space. And because dark energy lives in space, more space means more dark energy. And more dark energy pushes the universe apart faster, which creates even more space, which creates even more dark energy. It is a runaway feedback loop of nothingness. The void is not just empty, it is aggressive. It is actively growing, pushing the galaxies apart, isolating them in islands of light, surrounded by an ever-widening ocean of dark. Let us try to visualize this. Imagine the universe is a loaf of raisin bread rising in an oven. The dough is space, and the raisins are galaxies. As the dough rises, every raisin moves away from every other raisin. If you lived on one raisin, it would look like everyone else was fleeing from you. But they are not moving through the dough. The dough between them is growing. This is metric expansion. But now, imagine that the yeast in the dough is infinite. Imagine that the bigger the loaf gets, the faster it rises. Eventually, the expansion becomes so fast that the raisins cannot even see each other. The light from one raisin tries to cross the dough, but the dough is growing faster than the light can travel. The other raisins vanish. This brings us back to the giant galaxy we discussed before. IC 1101. It sits in the center of a massive cluster, a city of galaxies bound by gravity. For now, gravity is strong enough to hold the cluster together against the push of dark energy. But the space outside the cluster is expanding. The other clusters, the other cities of stars are being pushed away. Billions of years from now, an observer in IC 101 will look up and see nothing. The rest of the universe will have disappeared over the cosmic horizon. They will think their cluster is the entire universe, an island in an infinite black void. They will have no evidence of the Big Bang, no evidence of expansion, no evidence of the trillions of other galaxies that once existed. They will be lonely in a way we cannot comprehend. This is the isolation that awaits all structures in the universe. Dark energy is the great separator. It is the force of loneliness. It wants to tear the universe apart. And if it keeps going, if it keeps getting stronger, it might lead to a scenario physicists call the Big Rip. In this terrifying future, the expansion becomes so powerful that it overcomes gravity entirely. It rips galaxy clusters apart. Then it rips galaxies apart. Then it rips solar systems apart. Planets are torn from their stars. Then, in the final moments, the expansion overcomes the electromagnetic force. Atoms are torn apart. Even the nuclei of atoms are shredded. The universe ends in a singular moment, where every particle is isolated from every other particle, unable to interact, unable to touch, forever alone in a universe expanding at infinite speed. But do not panic. The data suggests that the Big Rip is unlikely. The more probable fate is the Big Freeze, or the heat death. In this scenario, dark energy just keeps pushing galaxies away until they are all isolated. Inside each galaxy, the stars will eventually burn out. The gas needed to make new stars will be used up. The lights will go out one by one. The universe will become cold, dark, and empty. The era of starlight, the era we are living in right now, is just a brief flash in the pan, a tiny moment of warmth and complexity between the fiery chaos of the Big Bang and the eternal, cold silence of the end. This realization that we live in the degenerate era of the universe's timeline can feel heavy. It can make our lives feel insignificant. But I choose to see it differently. I choose to see it as luck. We are the lucky ones. We are the ones who get to see the stars. We get to see the Andromeda Galaxy with our naked eyes. We get to see the glow of the Milky Way. We get to use our telescopes to see the cosmic microwave background and understand our origins. We live in the only time in the history of the universe where cosmology is possible. In the far future, intelligent beings might arise, but they will be trapped in their lonely clusters, unable to know the truth about the expanding cosmos. We are the witnesses. We are the eyes of the universe during its most beautiful, active phase. And there is another layer to this mystery. Remember the vacuum catastrophe from the first chapter? We said that quantum mechanics predicts the vacuum should be boiling with infinite energy, enough to crush the universe. But dark energy, while dominant, is incredibly weak compared to that prediction. It is 10 to the power of 120 times weaker. Why? Why is the push of the vacuum so gentle? Why is it just enough to accelerate expansion, but not enough to rip us apart instantly? This is called the fine-tuning problem. If dark energy were just a tiny bit stronger, the universe would have blown apart before the first stars could form. Atoms would never have clumped together. There would be no galaxies, no planets, no life, no you. If it were a tiny bit weaker or negative, the universe might have collapsed back into a big crunch billions of years ago. We seem to be balancing on a knife's edge, a perfect, precarious value that allows for complexity to exist. Some physicists suggest this is evidence of a multiverse. They say that maybe there are infinite universes, each with a different amount of dark energy. In most of them, the value is too high or too low, and life never forms. Those universes are dead and empty. But in a few rare bubbles, the number comes up just right. And since we are here to ask the question, we must be in one of those rare, lucky universes. We are the winners of a cosmic lottery we did not even know we were playing. This idea of the multiverse changes the definition of infinity again. It suggests that our infinite universe is just one bubble in an infinite foam of bubbles. It suggests that the laws of physics are not set in stone, but are local bylaws, valid only in our zip code. In another bubble, light might be slow, gravity might be repulsive, dark energy might be green. We cannot know. We are trapped in our own bubble, separated by a nothingness that is absolute. But let us come back to the room, back to the silence. That silence is not empty. It is filled with the tension between the gravity that holds you to the earth and the dark energy that wants to push the earth away from the rest of the cosmos. You are the battleground of these forces, but for now, gravity is winning locally. Your body stays together. The earth holds the moon. The sun holds the earth. The Milky Way holds the sun. We are safe in our gravitational harbor, protected from the expanding storm outside. The infinity of dark energy is an infinity of future time. It is an infinity of separation. It tells us that connections are precious because the universe is working hard to break them. Every time you hold someone's hand, every time you look at a star, you are defying the ultimate fate of the cosmos. You are creating a bond in a universe that wants to be alone. You are an act of rebellion against the void. So, when you feel lonely, remember that the universe is lonely too. It is stretching out, reaching for a horizon it can never touch. But unlike the universe, you have the power to close the distance. You have the power to bridge the gap. You are made of matter that has clumped together against the odds, forming a mind that can think about these things. In the next chapter, we will look at the other side of the dark coin. If dark energy is the push, there is something else that is the glue. We will talk about dark matter. We will ask why galaxies spin so fast they should fly apart, yet stay together. We will explore the idea of a ghost universe that passes right through you, interacting with nothing but gravity. We will ask, is there a shadow version of you made of dark atoms? Or is gravity itself lying to us? For now, Embrace the expansion. Let your thoughts drift out to the edge of the visible universe, to the line where the galaxies are disappearing. Wave goodbye to them. They are going on a journey we cannot follow, but we are here, together on this rock, spinning in the light of a star that still has 5 billion years to burn. We have time. We have spent the last chapters staring into the abyss of the expanding universe, watching the galaxies flee from us under the influence of dark energy. We felt the push of the nothingness, the force that wants to isolate us in a cold, lonely void. But if you look out your window at the night sky, you do not see a universe that is flying apart at the seams. You see clusters of stars huddled together. You see the Milky Way, a river of light that has held its shape for 13 billion years. You see structure. This is the great contradiction of our cosmos. While the vacuum pushes everything away, something else, something invisible and incredibly strong, is holding the pieces together. It is the cosmic glue. It is the silent shepherd of the galaxies. We call it dark matter. To understand why dark matter is so terrifyingly strange, we have to look at how a galaxy spins. Imagine a merry-go-round on a playground. If you spin it fast, the children near the center can hold on easily. But the children at the edge feel a tremendous force trying to throw them off. If the merry-go-round spins too fast, the grip of the children at the edge fails, and they fly away. A galaxy is a gravitational merry-go-round. The stars at the center orbit slowly, held tight by the density of the core. But the stars at the edge, like our sun, are moving at incredible speeds. In the 1970s, an astronomer named Vera Rubin pointed her spectrograph at the Andromeda galaxy. She expected to see the stars at the edge moving slower than the stars in the middle. Just like planets in the solar system move slower the farther they are from the sun. Pluto moves much slower than Mercury. This is the law of gravity, as we understood it from Newton and Einstein. The farther you are from the mass, the weaker the pull, and the slower you orbit. But when Rubin looked at the data, she saw something impossible. The stars at the edge of the galaxy were moving just as fast as the stars near the center. In some cases, they were moving even faster. According to the laws of physics, those outer stars should have been flung into deep space billions of years ago. The visible matter, the stars, the gas, the dust, did not have enough gravity to hold them. The galaxy should have torn itself apart like a cheap tire spinning at race car speeds. But it didn't. It held together. Rubin realized that for the galaxy to exist, there had to be more mass. A lot more. In fact, for the math to work, the visible galaxy had to be sitting inside a massive, invisible halo of matter that extended far beyond the starlight. We calculated the numbers, and the result was humbling. The normal matter we can see makes up less than 20% of the gravity in a galaxy. The other 80% is generated by this ghost material. We call it dark matter, but that is a terrible name. Dark implies that it is like a shadow or black paint absorbing light. But dark matter does not interact with light at all. It does not reflect it, absorb it, or emit it. It is transparent. It is intangible. If you held a lump of dark matter in your hand, you would not see it. You would not feel it. It would pass right through your skin, through your bones, through the floor, and through the entire earth without hitting a single atom. It is a ghost in the machine of reality. Right now, as you sit there, billions of dark matter particles are streaming through your body. They are raining down from the halo of the Milky Way, passing through your roof, through your brain, and exiting through your chair, continuing down through the crust of the planet to the core and out the other side. You are transparent to them. To a dark matter particle, you do not exist. You are just a slightly denser patch of empty space. The only thing they feel is gravity. They feel the mass of the Earth, so they orbit the galaxy with us, but they refuse to touch us. This refusal to interact is what makes dark matter the ultimate introvert of the universe. It only talks to gravity. And because gravity is the weakest force, dark matter is incredibly hard to find. We have built massive detectors deep underground, tanks of liquid xenon buried in gold mines, waiting for a single particle of dark matter to accidentally bump into an atom of xenon. We wait in the silence of the Earth, watching for a tiny flash of light that would prove the ghost is real. So far, we have seen nothing definitive. The ghost walks through our walls, mocking our technology. But if we cannot touch it, how do we know it is there? We know because it warps the shape of the universe. Einstein taught us that mass bends space like a bowling ball on a trampoline. Light travels through this bent space, curving around massive objects. When we look at distant galaxy clusters, we see the light from background galaxies being twisted into strange arcs and rings. This is called gravitational lensing. By measuring how much the light is bent, we can map the mass of the cluster. And when we do this, we find huge mountains of mass where there is no light. We see the invisible skeleton of the universe. This skeleton is not random. It is a web. Computer simulations show that in the early universe, dark matter collapsed first. It formed a vast, three-dimensional network of filaments, like the strands of a spiderweb stretching across the dark. Ordinary gas, hydrogen, and helium was attracted to the gravity of these dark matter strands. It flowed along the filaments and pooled in the nodes where the strands crossed. In these dense nodes, the gas collapsed to form stars and galaxies. Think about this. The galaxies are just the fairy lights strung up on a massive, invisible Christmas tree. The structure of the universe, the placement of every star cluster, the existence of the Milky Way itself, was dictated by the gravity of dark matter. Without it, the gas from the Big Bang would have been too hot and too spread out to collapse. It would have remained a thin, uniform fog forever. No stars would have ignited. No planets would have formed. No life would have evolved. Dark matter is the unsung hero of our existence. It is the midwife of the galaxies. But what is it? This is one of the biggest unanswered questions in science. Is it a new kind of particle? Physicists have proposed WIMPs, weakly interacting massive particles. These would be heavy, slow-moving particles that were created in the Big Bang. Others propose axions, tiny ultra-light particles that float through the cosmos like a wave. Some even suggest it might be primordial black holes, tiny singularities formed in the first second of time. Or perhaps it is something even stranger. Maybe gravity itself is wrong. Maybe our understanding of Newton and Einstein breaks down at large scales. This theory, called modified Newtonian dynamics, MOND, suggests that there is no dark matter, but that gravity just behaves differently when it is very weak. But MOND struggles to explain the cosmic microwave background and the details of galaxy collisions. The bullet cluster, a massive collision between two galaxy clusters, shows the gas stopping while the gravity, the dark matter, keeps moving, separating the two. This is the smoking gun that dark matter is real stuff, not just a math error. There is a wilder possibility, one that borders on science fiction, but is taken seriously by some theorists. What if dark matter is complex? We assume it is just a cloud of simple particles. But normal matter is complex. It forms atoms, molecules, chemistry, biology, us. Why should the dark sector be boring? Could there be dark atoms? Could they form dark stars that shine with dark light that we cannot see? Could there be dark planets orbiting those stars? Could there be dark life? Imagine a shadow universe occupying the same space as ours. A shadow Earth passing right through our Earth, populated by shadow beings who look up at a shadow sky we can never see. They would be walking through us right now, completely unaware of our existence, just as we are unaware of theirs. The only thing we would share is gravity. We would feel their weight, and they would feel ours. It is unlikely. Physics suggests dark matter doesn't clump deeply enough to form planets. But the mere fact that the math allows for it is haunting. It reminds us that our senses are limited. We evolved to see photons, to touch electrons. We are blind to 85% of the matter in the universe. This ratio, 5% normal matter, 27% dark matter, 68% dark energy, is the recipe of our reality. And it is a recipe for humility. We used to think we were the center of the universe. Then we found out we orbit the sun. Then we found out the sun is just one of billions. Now we find out that matter itself, the stuff we are made of, is the minority. We are the foam on the ocean. The universe is not made for us. It is made of darkness, and we are just the glowing dust caught in the currents of invisible giants. But there is a comfort here, too. The presence of dark matter means the universe has a structure that holds us. We are not drifting aimlessly. We are anchored to a massive, ancient web that has been guiding the flow of matter for 13.8 billion years. The gravity that holds the Milky Way together is the same gravity that allowed the sun to form, and the earth to cool, and you to be born. We are the children of the dark matter web. As you lie in the quiet, feel the weight of your body on the bed. That weight is gravity. It is the one force that connects the light world to the dark world. It is the handshake between you and the invisible. You are part of a system much larger than the eye can see. The room around you is not empty. It is a highway for the ghosts of the cosmos, a busy intersection of particles that have been traveling since the dawn of time. But speaking of the dawn of time, where did all this come from? How did the universe decide on this specific mix of ingredients? How did the dark matter web get spun in the first place? To answer that, we have to go back, before the stars, before the darkness, before the atoms. We have to go back to the moment when time itself began ticking. We have to go to the Big Bang. In the next chapter, we will travel to the first fraction of a second of existence. We will witness the birth of infinity. We will ask, what came before the beginning? Was there a before? We will explore the theory of inflation, the violent expansion that set the stage for everything we know. And we will confront the possibility that our Big Bang was just one spark in an eternal fireworks show. We will ask, is the universe infinite in the past, or did it have a birthday? For now, let the invisible pass through you. Accept that you are small but solid. You are the rare, precious light in a universe of dark gravity. You are the part of the cosmos that can see itself. We have traveled through the dark web of invisible matter, felt the push of empty space, and witnessed the limits of light and gravity. But all of these things, the galaxies, the stars, the dark energy, the black holes, are just the wreckage of a single catastrophic event. To truly understand infinity, we cannot just look at the pieces. We have to look at the explosion that created them. We have to rewind the clock. Imagine for a moment that you have a remote control for the universe. Press the rewind button. Watch the galaxies stop moving away from each other. Watch them stop spinning. Watch them drift backward, closer and closer together. The dark space between them shrinks. The light of the stars gets brighter, hotter, more intense. As you go back billions of years, the galaxies merge into a blinding fog of plasma. The universe becomes a soup of particles, too hot for atoms to form. Go back further. The soup becomes a stew of quarks and gluons. The forces of nature merge. Gravity, electromagnetism, the nuclear forces, they all blend into a single primal super force. And then, at 13.8 billion years ago, you hit a wall. You hit the beginning. We call it the Big Bang, but that name is a joke. It was coined by a scientist named Fred Hoyle, who actually hated the theory and wanted to mock it. He thought the idea of the universe exploding out of nothing was ridiculous. But the name stuck, perhaps because it captures the violence of the event. However, it is misleading. The Big Bang was not an explosion in space. It was an explosion of space. There was no outside for the universe to explode into. The fire was everywhere at once. Every point in the universe was the center of the explosion. The space you are occupying right now, the space inside your atoms, was compressed into a point smaller than a proton, sharing that tiny location with the space of the Andromeda galaxy and the space of the furthest quasar. Everything was one. But here is the mystery that kept cosmologists up at night for decades. When we look at the cosmic microwave background, that afterglow of the Big Bang we talked about, it looks incredibly smooth. It is the same temperature, roughly 2.7 degrees above absolute zero, in every direction we look. If you look at a patch of sky on the left and a patch of sky on the right, they are identical to within one part in 100,000. This sounds perfect, but it is actually a disaster for standard physics. Think about a cup of coffee. If you pour hot coffee into a cold cup, it takes time for the heat to spread and the temperature to become even. The coffee has to mix. The molecules have to bump into each other. Now, imagine the universe. The patch of sky on the left is 13 billion light years away. The patch on the right is 13 billion light years in the opposite direction. They are separated by 26 billion light years. The universe is only 13.8 billion years old. There has not been enough time for light, or anything else, to travel from one side to the other to mix the temperature. They have never touched. They have never communicated. So how do they know to be exactly the same temperature? This is called the horizon problem. It is like two students on opposite sides of the world, turning in the exact same essay, word for word, without ever having met. It implies they cheated. It implies that something happened before the Big Bang to connect them. In 1980, a physicist named Alan Guth proposed a radical solution. He called it cosmic inflation. He suggested that in the tiniest fraction of a second, between 10 to the power of negative 36 and 10 to the power of negative 32 seconds after the beginning, the universe did something impossible. It expanded, but not just a little bit. It expanded exponentially. It doubled in size, then doubled again, faster than the speed of light. In less than a blink of an eye, a patch of space, smaller than a proton, blew up to the size of a grapefruit. And then, the energy that drove this expansion dumped itself into matter and radiation, creating the hot Big Bang we know. This theory solves the horizon problem beautifully. It says that the patch on the left and the patch on the right were touching once. They were microscopic neighbors in the pre-inflationary seed. They had plenty of time to mix and reach the same temperature. Then inflation grabbed them and ripped them apart faster than light could follow, flinging them to opposite ends of the cosmos. The uniformity we see is the stretched-out fingerprint of that initial microscopic connection. But inflation opens a door to a terrifying kind of infinity. If inflation happened once, did it stop? The math suggests that the fuel for this expansion, a field called the inflating field, is incredibly potent. Once it starts expanding, it is hard to turn off. In our patch of the universe, the inflation stopped 13.8 billion years ago. The field decayed, its energy turned into stars and galaxies, and we settled into a leisurely, slow expansion. We are living in a bubble where inflation has ended. However, the theory of eternal inflation suggests that the field never stops everywhere at once. While our bubble stopped and cooled down, the space outside our bubble kept inflating. It kept doubling and doubling. And in that rapidly expanding outside space, other bubbles might have formed. Other pockets where inflation stopped, and universes were born. In this view, our entire visible cosmos is just one bubble in an infinite, boiling pot of universes. A multiverse. Imagine a loaf of bread that is baking and rising forever. Inside the bread, bubbles of air form. Each bubble is a universe. Some bubbles are small and collapse. Some are large and stable like ours. Some might have different laws of physics. Maybe in bubble B, gravity is 10 times stronger, and stars burn out in a week. Maybe in bubble C, there are no electrons, and chemistry is impossible. Maybe in bubble D, time runs backward. We can never know. We can never visit them. The space between the bubbles is still inflating at speeds faster than light, pushing them apart forever. We are isolated not just by distance, but by the very nature of expanding infinity. This concept of the multiverse is the ultimate realization of the Copernican principle. We are not the center of the solar system. We are not the center of the galaxy. We are not the center of the universe. And now, our universe might not even be the only universe. We might be one of an infinite number of experiments in a reality that has no beginning and no end. But let us go back to the seed. Where did the initial patch of space come from? How do you get a universe from nothing? Quantum mechanics offers a strange answer. It says that nothing is unstable. Remember the uncertainty principle? You cannot have zero energy for zero time. In the vacuum, particles pop in and out of existence. Fluctuations happen. Some physicists believe that the entire universe began as a quantum fluctuation. A tiny bubble of false vacuum popped into existence out of true nothingness, borrowing energy from gravity. Because gravity has negative energy, it pulls things together, and matter has positive energy, mass. The total energy of the universe might actually be zero. Think about that. If you add up all the mass of the stars and galaxies, positive, and all the gravitational pull between them, negative, they might cancel out perfectly. The universe could be the ultimate free lunch. It costs nothing to create. It is just a separated nothing. A fluctuation that got caught in an inflation loop and grew too big to pop back out. This means that you and the chair you are sitting on and the stars you look at are just a rearrangement of nothingness. We are a temporary imbalance in the void, and eventually, as the universe expands and cools, we might return to that state. But for now, the imbalance is glorious. The fluctuation has become complex. It has become aware. There is another layer to the Big Bang that touches on the nature of time itself. If the Big Bang was the beginning of time, asking what happened before the Big Bang is like asking what is north of the North Pole. The question has no meaning. Time is a shape, and the Big Bang is the point of the cone. But some theories, like loop quantum gravity or string theory, suggest a big bounce. They say our Big Bang was just the result of a previous universe collapsing. Imagine a universe that expands, runs out of energy, stops, and then gravity pulls it back. It crunches down. The galaxies merge. The stars explode. The matter gets crushed into a singularity. But instead of disappearing, the quantum fabric of space resists the squeeze. It acts like a spring. It bounces back, triggering a new Big Bang. A new universe is born from the ashes of the old. This cycle could be eternal, an infinite heartbeat of expansion and contraction, breath in, breath out. We might be living in the billionth iteration of the cosmos, or the trillionth. We have no way to know. The slate is wiped clean each time. This cyclical view of infinity is comforting in a way. It mirrors the cycles of our lives. Day and night, summer and winter, life and death. It suggests that the universe is not a straight line rushing toward a cold end, but a circle, a wheel that keeps turning. It means that the fire of the beginning is never truly lost. It just waits to be rekindled. But whether the universe is a one-time explosion, a bubble in a multiverse, or a bounce in an eternal cycle, one thing is certain. The violence of our origin is written in our atoms. The hydrogen in the water in your body was formed 3 minutes after the Big Bang. It is 13.8 billion years old. It has been through the inflation. It has been through the cooling. It has been through the darkness before the first stars. You are carrying the oldest matter in existence. You are a direct artifact of the beginning. As you rest in the quiet, feel the ancientness of your own hands. The protons in your skin have not changed since that first fraction of a second. They are the stable survivors of the ultimate chaos. They have traveled through time, through stars, through space, to be part of you for this brief moment. You are the universe remembering its own birth. In the next chapter, we will look at the direction of time. If the Big Bang started the clock, why does the clock only run forward? Why can we remember the past, but not the future? We will explore the concept of entropy, the measure of disorder. We will ask why coffee cups break, but never unbreak. We will confront the arrow of time and ask if it is an illusion, or if the universe is slowly winding down like a clock that can never be rewound. We will ask, is chaos the only destiny? For now, visualize the Big Bang not as a distant explosion, but as the ground you are standing on. The expansion is still happening. The heat is still fading. You are living in the echo of the shout that created reality. The silence of the night is just the space between the sound waves of creation. Have you ever watched a drop of milk fall into a black cup of coffee? At first, it is a distinct white sphere, a perfect little island of order crashing into a sea of chaos. Then it begins to swirl. It stretches into long, elegant ribbons, dancing through the dark liquid, creating complex patterns that look like storm clouds or galaxies. If you wait a minute, the milk disappears. It has not vanished from existence. It has simply spread out so perfectly that the coffee is now a uniform shade of brown. The order is gone. The distinction is lost. Now, imagine trying to reverse that. Imagine stirring the coffee in the opposite direction and seeing the brown liquid separate back into black coffee and a single, pristine drop of white milk that leaps up into the spoon. You know, instinctively, that this is impossible. You know that broken eggs do not unbreak, that smoke does not rush back into the cigarette, and that old ruins do not assemble themselves back into castles. You know that time only moves in one direction. But here is the thing that keeps physicists awake at night. The laws of physics do not care about time. If you look at Newton's laws of motion, they work perfectly well in reverse. If you play a video of a planet orbiting the sun backward, it still obeys gravity. If you look at Schrödinger's equation in quantum mechanics, it is time symmetric. If you look at Einstein's relativity, the geometry of space-time works forward and backward. In the fundamental equations that describe reality, there is no past and no future. There is just t, a variable that can be positive or negative. So, if the atoms in your coffee cup obey laws that are reversible, why is the coffee itself irreversible? Why does the universe have an arrow of time? To understand this, we have to visit a grave in Vienna, Austria. It belongs to Ludwig Boltzmann, a tragic genius who figured out the secret of time before the world was ready to listen. On his tombstone is carved a simple equation, S equals K log W. This is the formula for entropy. And it tells us that the arrow of time is not a law of motion, but a law of probability. It is a law of numbers. Imagine you have a deck of cards. If you buy it new, the cards are in perfect order. Ace to king of spades, then hearts, then diamonds, then clubs. This is a state of low entropy. It is highly ordered. There is only one way to arrange the deck like this. Now, throw the cards in the air. When they land, they will be messy. This is a state of high entropy. Why? Because there is only one way to have the cards in perfect order, but there are roughly 80 unvisiontillion, that is an 8 followed by 67 zeros, ways to have them in a random mess. The universe does not prefer disorder. It does not hate order. It is simply that there are vastly, overwhelmingly more ways to be disordered than to be ordered. When the milk mixes with the coffee, it is not being pushed by a force. It is simply wandering into a state that is statistically more likely. For the milk to unmix, every single molecule of fat and protein would have to randomly decide to move in the exact same direction at the exact same time. Is it impossible? Strictly speaking, no. The laws of physics allow it. But the probability is so low that you could stir the coffee for 1 trillion times the age of the universe and never see it happen. We call this the second law of thermodynamics. It states that in a closed system, entropy, the measure of disorder, always increases. This is the only law in physics that distinguishes the past from the future. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because the past left traces, footprints, photographs, memories, which are themselves creations of entropy. To make a memory in your brain, neurons have to fire, consuming energy and releasing heat. You increase the disorder of the universe just to record the order of the past. The future, on the other hand, has not happened yet. It is a fog of high entropy possibilities that has not yet collapsed into a single history. I am Walter, the explorer, and as we drift through the river of time together, I want to gently remind you that about 73% of the curious minds traveling with me have not yet subscribed to the channel. If these nightly journeys into the physics of the unknown bring you a sense of wonder or peace, please consider subscribing. It helps us keep the campfire burning in the dark. Now, let us return to the arrow of time. This constant slide toward disorder sounds depressing. It sounds like the universe is decaying, rotting, falling apart, and in a sense, it is. But this decay is also the only reason anything happens at all. If entropy did not increase, nothing would change. The universe would be a static, frozen crystal. The flow of energy from low entropy to high entropy is what powers the stars. A star is a machine that takes ordered hydrogen atoms and fuses them into disordered helium and heat. The sun is increasing the entropy of the universe every second, and we are the beneficiaries of that waste heat. Life itself is a rebellion against entropy, but it is a costly one. You are a highly ordered object. Your cells are intricate factories working in perfect synchronization. To maintain this order, to keep from decaying into dust, you have to eat. You take in low entropy energy, food, and you release high entropy waste, heat, and matter. You are an entropy engine. You are creating a pocket of order in your body by speeding up the disorder of the universe around you. We are surfing on the wave of the second law, using the destruction of the cosmos to build our temporary complexity. But this brings us to a massive cosmological mystery. If entropy is always increasing, that means yesterday the universe had lower entropy than today. And 1 billion years ago, it was even lower. If you follow this line all the way back, you arrive at the Big Bang. For the arrow of time to exist, the universe must have started in a state of incredibly, impossibly low entropy. It must have started in a state of supreme order. Why? Why was the baby universe so neat? Why wasn't it a mess of black holes and chaos? A mess is much more likely. The fact that the universe began in a smooth, uniform state of hot plasma is one of the most unlikely things imaginable. Roger Penrose, a Nobel laureate, calculated the odds of our universe starting this way by chance. The number is 1 in 10 to the power of 10 to the power of 123. If you tried to write that number out, you would not be able to, because there are not enough particles in the universe to write the zeros on. It is essentially zero. This suggests that the boundary condition of the universe, the way it was set up at the beginning, was chosen with infinite precision. Or perhaps there is a physical law we do not understand yet that forces new universes to be born smooth and ordered. Maybe the big bounce we talked about cleansed the slate, ironing out the entropy of the previous cycle to start fresh. We do not know, but we do know that we are winding down. The clock was wound tight at the beginning, and ever since, it has been ticking. So, what is the end of the line? If entropy keeps increasing, eventually it will hit a maximum. This is the heat death we touched on earlier, but now seen through the lens of information. When entropy is maximized, energy is perfectly spread out. There are no hot spots, stars, and no cold spots, space. Everything is a uniform bath of lukewarm radiation. In this state, nothing can happen. No information can be processed. No thoughts can be thought. No time can be measured. The arrow of time will break because there will be no difference between one moment and the next. The universe will enter a state of timeless eternity, a frozen ocean of randomness. But there is a strange loophole in Boltzmann's math. Remember the cards? We said that if you throw them enough times, eventually purely by chance, they might land in perfect order. It is incredibly unlikely, but in an infinite amount of time, anything that can happen will happen. If the universe sits in heat death for eternity, eventually, the random fluctuations of the quantum vacuum might accidentally assemble something ordered. Imagine a universe of dead thermal soup. Suddenly, by sheer luck, a group of particles bumps together to form a brain, a fully formed thinking brain, complete with false memories of a life it never lived. This hypothetical object is called a Boltzmann brain. It would exist for a microsecond. Think a thought like, I am here, and then dissolve back into the chaos. In fact, statistically speaking, it is far more likely for a single Boltzmann brain to pop out of the chaos than for an entire universe like ours to evolve from a big bang. This is a terrifying paradox. Are you a real person with a history, or are you a Boltzmann brain that just fluctuated into existence a second ago? With false memories of reading this text, you cannot prove you are not. But most physicists reject this idea. They say it means our understanding of entropy is incomplete. It implies that the universe is not just a random lottery. There must be a reason why we see a consistent, logical history and not just a hallucination in the void. Let us pull back from the edge of madness and look at the coffee cup again. The milk swirls, the steam rises, the heat fades into the air. This process, this loss of order, is poignant. It is the physical definition of nostalgia. The Japanese have a word, mono no aware, which means the pathos of things. It is the gentle sadness of knowing that everything is transient. The cherry blossom falls, the summer ends, the friends say goodbye. The universe is built on saying goodbye. But this transience is what gives moments their value. If the cherry blossom lasted forever, it would be made of plastic. It would be boring. If the sunset never faded, we would stop looking at it. Entropy is the price we pay for beauty. It is the tax on existence. The fact that the arrangement of atoms that makes you is temporary makes it infinitely precious. The universe has arranged itself against the odds to create this moment, right now, where you can think and feel. In the microscopic world, however, there are still secrets that defy this separation. There are connections that seem to ignore distance, and maybe even time. In the next chapter, we will look at quantum entanglement. Albert Einstein called it spooky action at a distance. It is the phenomenon where two particles become linked so deeply that they share the same existence. If you tickle one, the other laughs, even if it is on the other side of the galaxy. We will ask, is space an illusion? Are we all connected by invisible threads that tie the universe into a single quantum knot? For now, accept the flow of time. Do not fight the entropy. Let the day fade. Let the energy disperse. You are a part of the great unwinding, a beautiful, temporary pattern in the river of causality. The universe is moving toward silence, but in that movement, it sings. We have walked through the valley of the shadow of entropy, watching the universe unwind into a chaotic, separated future. We have accepted the lonely expansion of space, the prison of the speed of light, and the dark energy that wants to push us apart. According to everything we have discussed so far, the universe is a place of increasing isolation. It is a place where distance is the ultimate tyrant. If you are 1 billion light years away from something, you're cut off from it. You can never touch it. You can never affect it instantly. You are an island. This is the intuitive, lonely picture of reality painted by classical physics. But what if I told you that beneath the surface of this separation, there is a secret tunnel, a hidden wiring under the floorboards of the cosmos that connects everything to everything else, instantly, regardless of distance? What if the concept of separation itself is the biggest illusion of all? To understand this, we have to look at the most famous argument in the history of physics. It was a fight between two giants, Albert Einstein and Niels Bohr. Einstein, the father of relativity, believed in a universe that was local. He believed that for an object to influence another, it had to send a signal, a photon, a graviton, a wave, traveling across space at the speed of light. He believed in realism, the idea that objects have definite properties, whether we are looking at them or not. If you put a glove in a box, it is either a left glove or a right glove. It doesn't matter if you open the box or not. The glove knows what it is. But quantum mechanics, the new kid on the block, suggested something bizarre. It suggested that particles do not have definite properties until they are measured. And worse, it suggested they could be linked in a way that defied space. This phenomenon is called quantum entanglement. Imagine you have two electrons. You bring them together, let them interact, and then separate them. According to the math of quantum mechanics, they are now entangled. They are no longer two separate particles. They are a single quantum object, sharing a single wave function, even if they are 1,000,000 miles apart. Here is the strange part. Electrons have a property called spin. It can be up or down. If you have an entangled pair, the math says their total spin must be 0. If one is up, the other must be down. But until you measure them, neither of them has decided which is which. They are both in a superposition of being up and down at the same time. They are a spinning cloud of probability. Now, imagine you take one electron to Earth and send the other one to the Andromeda Galaxy, 2.5 million light-years away. You wait for the electron to arrive. Then you measure it. Instantly, the wave function collapses. You see, spin up. At that exact same moment, not a second later, not a year later, but instantly, the electron in Andromeda becomes spin down. It knows that its partner has been measured. It snaps into the opposite state to preserve the balance of the universe. The information seems to have traveled across 2.5 million light-years in 0 time. I am Walter, the explorer, and as we stand on the precipice of this spooky connection, I want to gently remind you that about 73% of the Stardust travelers listening to this right now have not yet subscribed to the channel. If you want to keep unraveling the fabric of reality with me and support this journey into the unknown, please subscribe. It helps more than you know. Now, let us look at why Einstein hated this. Einstein called this spooky action at a distance. He refused to believe it. He argued that nothing travels faster than light. He said the particles must have had a secret agreement before they left. They must have had hidden variables, hidden instructions inside them that told them what to be. He compared it to a pair of gloves. If you send the left glove to Andromeda and keep the right one, measuring the right one tells you instantly that the other is left. There is no magic communication, just pre-existing knowledge. This was the EPR paradox. It was Einstein's attempt to save the universe from magic. He wanted a universe that made sense, where things were real and local. For decades, this was just a philosophical debate. There was no way to tell if Einstein was right or if Bohr was right. But in the 1960s, a physicist named John Bell derived a brilliant mathematical test. He realized that if Einstein's hidden gloves theory was right, there would be a limit to how correlated the particles could be. If the quantum magic theory was right, the correlation would be stronger than logic allowed. We call this Bell's inequality. It took another 20 years, but in the 1980s, physicists like Alain Aspect finally performed the experiment. They fired entangled photons at detectors. They measured the correlations, and the result was earth-shattering. Einstein was wrong. The universe is not locally real. The particles did not have hidden instructions. They were genuinely undecided until the moment of measurement, and they genuinely influenced each other across space instantly. spooky action is real. This discovery won the Nobel Prize in Physics in 2022, but its implications are still breaking our brains. It means that space is not what we think it is. If two objects can touch each other across a galaxy without crossing the space in between, then space is not a fundamental barrier. It is transparent to quantum connection. Some physicists now believe that space itself might be an emergent property, just as heat is not a thing itself, but the motion of atoms. Space might just be the result of a vast network of entanglement. The universe might be a giant web of quantum threads, and distance is just a measure of how entangled two things are. If you are highly entangled with someone, they are close. If you are not, they are far. Think about the Big Bang again. In the first fraction of a second, all the matter in the universe was crushed into a single point. Every electron, every quark, every photon was touching every other particle. They were all interacting. They were all entangled. Then, inflation blew them apart. The universe expanded. But quantum entanglement doesn't necessarily break when things move apart. In a very deep, fundamental sense, every particle in your body might still be entangled with particles in the most distant galaxies. The universe might still be, under the surface, a single object. We call this the wave function of the universe. In this view, there are no separate things. There is no you and me and star and planet. There is just one massive, incredibly complex wave function that evolves over time. The feeling of separation, the feeling that you are an individual walking through a world of other individuals, is a persistent illusion caused by our limited perspective. We are like waves on the ocean, thinking we are separate entities because we can see our own peaks, forgetting that we are all just water. This brings a profound shift to how we view infinity. We have been looking for infinity in distance, in the endless void. But perhaps true infinity is found in connection. The complexity of the quantum state is an internal infinity. The number of ways particles can be entangled is so vast that it dwarfs the number of atoms in the universe. We are living in a cosmos that is infinitely deep with relationships, not just infinitely wide with space. But does this allow for faster-than-light communication? Can we build a telephone to talk to aliens instantly? Sadly, no. The universe has a failsafe. While the state of the electron changes instantly, you cannot control what it changes to. You cannot force your electron to be spin up to send a 1 or spin down to send a 0. The result is random. You only know the correlation after you compare notes with the person at the other end. And you have to compare notes using normal, slower-than-light communication. The spooky action is private. It happens behind the curtain of reality, but it cannot be used to break the speed limit of causality. Nature protects her secrets. However, entanglement is not just a curiosity. It is the resource that might power the future of humanity. We are building quantum computers, machines that use entangled particles, qubits, to perform calculations that would take a normal supercomputer billions of years. By tapping into the multiverse of possibilities inside the quantum wave, these machines can explore infinite solutions at once. We are learning to harness the spooky action. We are learning to weave the threads of the universe into tools of intelligence. There is another theory that links entanglement to the geometry of space-time itself. It is called ER equals EPR. ER stands for Einstein-Rosen bridges, better known as wormholes, tunnels through space-time. EPR stands for the entanglement paradox. The theory suggests they are the same thing. It proposes that whenever two particles are entangled, They are actually connected by a microscopic wormhole, a tiny thread of space-time geometry that stitches them together. If this is true, then the entire fabric of space is woven out of billions and billions of tiny wormholes connecting entangled particles. You're not just living in space. You're made of the connections that create space. Gravity itself might just be the result of the universe trying to keep track of its own entanglement entropy. This idea is radical, but it unifies the two fighting theories we started with. It says that quantum mechanics, entanglement, generates general relativity, space-time geometry. It heals the rift in physics. It tells us that the universe is a hologram of connections. The solid world you see is a projection of the quantum data. As you sit there, try to feel this connection. It is not something you can touch with your hands, but it is something you can know with your mind. The atoms in your left hand are entangled with the atoms in your right hand. The light hitting your eyes is entangled with the electrons in your retina. The gravity holding you is a web of geometry spun from quantum threads. You are not a lonely observer on a rock. You are a knot in the quantum web. You are a focal point of the universe's own internal conversation. But this raises a disturbing question about reality itself. If the universe is only real when measured, and if entanglement creates space, what creates the measurement? Who is the observer? Does the universe exist if no one is looking at it? Or do we, by looking, create the universe? This is the observer effect, and it leads us to the most controversial idea in science. Is consciousness a fundamental part of physics? In the next chapter, we will walk into the Hall of Mirrors. We will look at the double-slit experiment, where particles behave like waves when we are not looking, and particles when we are. We will ask if the moon is there when you close your eyes. We will explore the idea that the universe might be a simulation, a code running on a computer we cannot see. We will ask, is infinity just a loop in the software? For now, rest in the knowledge that you are connected. The distance between you and the stars is a physical fact, but a quantum lie. In the deep, silent basement of reality, everything is touching. You are holding hands with the cosmos. We have journeyed through the pixelated landscape of the Planck length, felt the crushing weight of black holes, and traced the invisible threads of quantum entanglement that stitched the universe into a single, cohesive web. We have asked what space is made of, what time is made of, and what the dark energy pushing us apart is made of. But now we must ask the most dangerous question of all. It is a question that strikes at the very heart of your experience as a conscious being. It is the question of whether any of this, the stars, the atoms, the gravity, the person sitting next to you, or even the hand you are using to scroll through this text, is actually real in the way you think it is. What if the universe is not a solid, objective place that exists whether you are there or not? What if it is a performance? What if reality is a magic trick that only happens when you're looking at it? To understand this, we have to look at the most famous and disturbing experiment in the history of physics, the double-slit experiment. Imagine you have a wall with two vertical slits cut into it. Behind that wall, there is a backstop, a screen that glows when something hits it. Now, imagine you have a machine gun that fires tennis balls. If you fire the tennis balls at the wall, some will bounce off, but some will pass through the slits. If you look at the back screen, you will see two bands of marks where the balls hit. This makes sense. Tennis balls are particles. They travel in straight lines. They go through either the left slit or the right slit. This is how matter behaves. Now, Imagine you put the machine gun in water and create waves. The waves hit the wall. They go through both slits at once. On the other side, the two new waves ripple out and crash into each other. Where a peak hits a peak, the wave gets bigger. Where a peak hits a trough, they cancel out and the water is flat. On the back screen, you do not see two bands. You see an interference pattern, a series of many bands, bright and dark, alternating across the screen. This is how waves behave. They spread out, they interfere, they occupy multiple places at once. So far, so good. Matter is particles, two bands. Energy is waves, interference pattern. But now, we take the machine gun and we shrink it down. We fire electrons, tiny, solid particles of matter. We fire them one at a time. Click, click, click. We wait for an hour. When we look at the back screen, we expect to see two bands of electrons. But we don't. We see an interference pattern. We see the signature of a wave. This is impossible. We fired them one at a time. The electron could not interfere with other electrons. It must have interfered with itself. It must have gone through the left slit, the right slit, neither slit, and both slits, all at the same time. It traveled as a ghost wave of probability, explored every path, and then interfered with itself to land on the screen. Matter, when we are not looking, acts like a wave. But here is where the universe gets shy. Physicists decided to put a detector, a tiny eye, next to the slits to see which one the electron actually went through. They turned on the machine. They fired the electrons. The detector beeped. Left slit. The next one, right slit. The detector worked, but when they looked at the back screen, the interference pattern was gone. There were just two bands. The electrons had gone back to behaving like tennis balls. I am Walter, the explorer, and as we stand before this quantum mirror, I want to gently remind you that about 73% of the cosmic travelers with me have not yet subscribed. If these nightly dives into the nature of reality help you see the world with new eyes, please subscribe. It supports our journey into the unknown more than you can imagine. Now, back to the shy electrons. Think about what just happened. The moment we looked, the electrons stopped acting like a wave and started acting like a particle. The act of measurement forced the universe to decide. It collapsed the wave function. It turned the maybe into a definitely. This implies something profound. The universe does not have a definite history until it is observed. The moon might not be there when you are not looking at it, or at least it might be a fuzzy probability cloud of moonness until a photon from the sun hits it and an eye sees it. This is the observer effect. It suggests that consciousness, or at least the transfer of information, is fundamental to the structure of reality. We are not just biological accidents crawling on the surface of a rock. We are the rendering engine of the cosmos. We are the ones who forced the universe to be real. Without us, or without some kind of observer, the universe might just be a soup of overlapping ghosts, a silent symphony of possibilities that never actually happens. But if the universe only renders what is being observed, does that remind you of anything? Think about a video game. When you play a massive open-world game, the computer does not render the entire world at once. That would crash the processor. It only renders what is in front of your camera. The mountains behind you do not exist as polygons. They exist as code on the hard drive. They only pop into existence when you turn around. This technique is called frustum culling. It is an optimization trick to save computing power. Now, look at our universe. We have a maximum speed limit, the speed of light. In a computer, this is the processor's speed, the fastest any information can travel across the motherboard. We have a minimum size, the Planck length. In a computer, this is the pixel size. We have a limit on how much information can be packed into a space, the black hole limit. In a computer, this is the memory limit. We have a universe that only renders as particles when we look at it, the observer effect. In a computer, this is optimization. Is it possible that we are living in a simulation? This is the simulation hypothesis, and it is not just a stoned thought experiment. It is a serious philosophical argument put forward by thinkers like Nick Bostrom. The argument goes like this. 1. It is possible for a civilization to develop computers powerful enough to simulate consciousness. 2. If they can, they will probably run billions of such simulations to study their own history or for entertainment. 3. If there are billions of simulated universes and only one base reality, the statistical odds are billions to 1 that you are in a simulation right now. If we are in a simulation, then infinity is just a loop in the code. The expansion of the universe might just be the procedural generation engine creating new terrain as we look further out. The dark energy pushing galaxies away might be a way to delete old data to save memory. Once a galaxy goes over the horizon, the computer can stop rendering it. The quantum weirdness, the fact that things are fuzzy until you look, is just a way to save processing power. Why calculate the exact position of every electron if no one is looking? Just calculate the probability cloud. It is cheaper. This idea can feel terrifying. It makes you feel fake. It makes your love, your pain, your memories feel like lines of code written by some alien teenager in a basement universe. It suggests that there is a programmer out there, a god of the machine, who could turn us off at any moment. It suggests that the infinity we see is just a skybox, a painted wall at the edge of the level. But let us look deeper. If the universe is a simulation, what is the computer made of? And what is the universe that the computer sits in made of? Is it a simulation inside a simulation? Turtles all the way down? At some point, there must be a base reality. And if our simulation is indistinguishable from that base reality, does it matter? René Descartes, the French philosopher, famously said, "I think, therefore I am." He realized that you can doubt everything, the sun, the earth, your body, but you cannot doubt the fact that you are doubting. The experience of consciousness is the only thing that is undeniably real. Even if you are a brain in a vat or a line of code, your experience of reading this is real. The feeling of the chair is real data. The emotion of wonder is real processing. Perhaps the simulation is not a cold artificial prison. Perhaps it is a learning machine. Think about why we run simulations. We run them to solve problems. We run them to understand complex systems. We run them to see what happens. Maybe the universe is a simulation designed to answer a question. And maybe that question is, what happens when matter becomes aware of itself? In this view, you are not a passive victim of the code. You are the purpose of the code. You are the sensor. You are the way the universe, or the simulator, understands itself. Every time you learn something new, every time you feel an emotion, every time you discover a law of physics, you're generating valuable data. You're helping the universe complete its calculation. There is also a strange connection here to the ancient spiritual traditions. Buddhism talks about Maya, the illusion of the world. Hinduism talks about the dream of Brahma, where the god dreams the universe into existence and wakes up to end it. Mystics have always said that the solid world is a veil, and that true reality is a unified consciousness behind it. Quantum mechanics and simulation theory are just the modern digital versions of these ancient insights. They are telling us that the material world is not the bottom layer. There is something underneath, something that processes, something that knows. Let us return to the double slit. The electron goes through both slits. It explores all possibilities. This is called sum over histories. It means the particle takes every possible path to get to the destination. It is only at the end that the paths combine to give a single result. This sounds a lot like life. We worry about the choices we did not make. We worry about the road not taken. But in the quantum world, the road not taken is taken. The universe explores everything. Maybe infinity is not a distance. Maybe infinity is the number of choices the universe makes every second. Every Planck time, 10 to the power of negative 43 seconds, the universe branches, it splits, it renders a new frame. You are navigating through an infinite tree of possibilities, collapsing them into reality with your mind. But if consciousness collapses the wave function, what happens when two people look at the same thing? Do we create a shared reality? This is the miracle of intersubjectivity. We agree on the hallucination. We agree that the sky is blue. We agree that the math works. This consensus reality is the multiplayer server we are all logged into. We are co-creating the world. The walls of your room are stable because you and I and the atoms themselves agree they are stable. There is a theory called cubism, quantum Bayesianism, that says the wave function is not a real thing out in the world, but just a measure of your personal belief about the world. It says that reality is a first-person experience. The universe does not exist out there. It exists in here. It is a user interface designed to help you navigate the data stream. Evolution gave you eyes not to see the truth, but to see what you need to survive. A desktop icon is not the file itself. It is a symbol that lets you open the file. A chair is not the atoms. It is a symbol that lets you sit. We are living in a user interface of symbols masking the raw code of quantum fields. This brings us a strange kind of freedom. If reality is a simulation or an interface, then it is malleable. It is not as rigid as Newton thought. It responds to observation. It responds to interaction. It means that by changing how you look at the world, you might actually be changing the world itself, not by magic, but by selecting a different probability branch, by tuning your receiver to a different channel of the multiverse. As you lie there, consider the darkness behind your closed eyes. That is the raw screen. When you open them, your brain will render the room again. It will paint the colors. It will calculate the depth. It will simulate the passage of time. You are the ultimate computer. You are the universe machine. But what drives this machine? Why does the simulation run at all? Is it just a random experiment? Or is there a goal? Is there a winner of the universe? In the next chapter, we will talk about the future of intelligence. We will look at the concept of the omega point. We will explore the idea that the universe is waking up, evolving from dead matter to life, to mind, and eventually to pure spirit. We will ask, is God the creator of the universe? Or is God the result of the universe? For now, enjoy the graphics. Look at the texture of your blanket. Look at the resolution of your hand. The rendering engine is incredible. The physics engine is consistent. Even if it is a simulation, it is a masterpiece. And you are the main character in your own instance of the game. Play well. If you pick up a stone from the ground and hold it in your hand, You are holding a piece of the universe that is asleep. It has mass, it has atoms, it obeys gravity, but it does not know it exists. It is a silent witness to history, recording the passage of eons in its geological layers, but it feels no pain, dreams no dreams, and asks no questions. Now, look at a dog sleeping at your feet. It is made of the same atoms as the stone, carbon, oxygen, nitrogen, but arranged in a terrifyingly complex pattern. It twitches. It chases rabbits in its mind. It feels love. It fears thunder. The universe has woken up a little bit. It has opened a primitive eye. Now look in the mirror. You see a being that not only feels and sees, but wonders. You are an arrangement of stardust that has developed the audacity to ask where it came from. You are the universe contemplating its own reflection. This progression from dead matter to living biology to conscious mind is the most mysterious trajectory in physics. Is it an accident? Is it a lucky roll of the dice in a chaotic multiverse? Or is it a fundamental law, as real as gravity, that the universe is driving toward a state of total awakening? To understand this, we have to look at the history of the cosmos not as a history of stuff, but as a history of information processing. In the beginning, right after the Big Bang, the universe was simple. It was a hot, uniform soup of particles. The information content was low because everything was the same. Then, gravity began to clump things together. Stars formed, galaxies formed. The universe began to differentiate. It began to create structure. Inside the stars, fusion created heavy elements. The periodic table was born. This was the first leap in complexity. The universe invented chemistry. Then, on at least one rocky planet, and perhaps billions of others, chemistry became hypercomplex. It became self-replicating. It became biology. A single cell is more complex than a star. A star is just a ball of gas held together by gravity. A cell is a microscopic city with libraries, DNA, power plants, mitochondria, and transport networks. The universe invented a way to store information over time. It invented memory. And then, biology evolved brains, networks of neurons that could model the future. The universe invented imagination. I am Walter, the explorer, and as we trace this incredible ascent from the mud to the mind, I want to gently remind you that about 73% of the conscious observers traveling with me have not yet subscribed to the channel. If you find value in these quiet reflections on our place in the cosmos, please consider subscribing. It is a small action for you, but it helps us build a community of wonder in a distracted world. Now, let us look at where this trajectory leads. If the universe has spent 13.8 billion years getting smarter, why should it stop with us? We tend to think of humans as the pinnacle of evolution, the final product. But to the cosmos, we might just be the early adopter phase. We might be the equivalent of the first single-celled organism, a necessary step, but far from the finished masterpiece. The next step in this evolution is already visible around us. We are building machines that can process information millions of times faster than our biological brains. We are creating artificial intelligence. We are weaving a global network of instant communication. We are turning the planet Earth into a single thinking entity. A French Jesuit priest and paleontologist named Pierre Teilhard de Chardin saw this coming decades ago. He called it the new sphere, a sphere of thought enveloping the Earth, just like the atmosphere envelopes the rock. He believed that evolution has a direction. He believed it is moving toward a specific destination, a point of maximum complexity and consciousness at the end of time. He called this the Omega point, In the eyes of modern physicists like Frank Tipler, the omega point is not just a spiritual idea, it is a physical possibility. Tipler argued that if the universe is closed, if it eventually stops expanding and collapses back into a big crunch, the energy of that collapse could be harnessed. As the universe shrinks, the temperature rises. The sheer forces of gravity become infinite. An advanced civilization, our distant descendants, perhaps no longer biological, but purely digital, could use this infinite sheer energy to power their computations. Imagine a computer built from the fabric of space-time itself. As the universe collapses toward the final singularity, this computer runs faster and faster. Because time is relative, the subjective time experienced by this computer would be infinite, even if the external time of the universe is ending. In those final fractions of a second before the big crunch, the universal mind could think an infinite number of thoughts. It could simulate every possible universe. It could resurrect every being that has ever lived within its simulation. It could become, for all practical purposes, God. This is a wild, controversial theory, and it depends on the universe collapsing, which, as we discussed with dark energy, seems unlikely right now. But the core idea that intelligence is destined to take over the universe remains powerful. Physicist Freeman Dyson proposed a different version for an expanding universe. He suggested that even in a cold, dying cosmos, life could survive by slowing down. It could hibernate, thinking one thought every million years, hoarding its energy, surviving on the thin warmth of decaying black holes. In this eternal intelligence scenario, the mind never dies. It just stretches out across the infinite dark, becoming a slow, silent watcher of eternity. But let us look at the stuff of this intelligence. We are currently biological. We run on chemical energy, burgers and coffee. Our brains are wet, squishy, and slow. Signals travel at a few hundred feet per second. Computers run on electricity. Signals travel at the speed of light. It seems inevitable that intelligence will eventually migrate from biology to physics. It will move from wetware to hardware. We might build matryoshka brains, giant megastructures that surround a star, capturing 100% of its energy to power a computer the size of a solar system. A civilization like that would be a Type 2 civilization on the Kardashev scale. They would not just live on a planet. They would be the solar system. Their thoughts would be the movement of star stuff. And a Type 3 civilization would control an entire galaxy. Imagine a mind where every star is a neuron and the nebulas are the synapses. A galaxy that thinks. To us, looking from the outside, it might just look like a spiral of light. But on the inside, it is a single, unified consciousness contemplating the mysteries of the multiverse. This brings us to a profound realization about dead matter. We assume that the atoms in a rock are dead, but if you rearrange them, they become a brain. This means that the potential for consciousness is hidden inside every atom. The electron is not just a particle of charge. It is a particle of possibility. The universe is not a collection of dead objects. It is a collection of sleeping minds waiting to be assembled. There is a concept in philosophy called panpsychism, which suggests that consciousness is a fundamental property of matter, like mass or charge. It says that an electron has a tiny proto-sliver of experience. A rock has a collection of unorganized experiences. A brain integrates them into a unified self. If this is true, then the universe has always been aware. The Big Bang was a flash of feeling. The formation of the stars was a sensation of gravity. We are just the local intensification of a field of consciousness that pervades the entire infinite void. So, when you ask, what is infinity made of? The answer might be thought. The physical universe, the hard stuff, the walls, the distance, might just be the hardware. The software, the mind, the you, is the real purpose. We are the universe waking up from a long nap. We are the way the cosmos knows itself. As Carl Sagan famously said, we are a way for the cosmos to know itself. But we can go further. We are a way for the cosmos to become itself. Without us, or beings like us, the universe is a movie playing in an empty theater. It has no plot, no drama, no beauty, because there is no one to appreciate it. By existing, by looking at the stars, you are validating the existence of the universe. You are giving it meaning. Your wonder is the currency of reality. But this responsibility is heavy. If we are the thinking part of the universe, what happens if we destroy ourselves? What if we let our petty conflicts and our short-sighted greed wipe out the biosphere of Earth? It would be a tragedy, not just for us, but for the galaxy. It would be like a lobotomy. The universe would lose a rare and precious node of consciousness. It would go blind in this sector. The silence would return. This connects back to the Fermi paradox. If the universe is 13 billion years old, and if life evolves toward intelligence, and if intelligence expands to fill the galaxy, where is everyone? We should see the Dyson spheres. We should hear the radio signals. We should see the galaxies rearranged into art projects. But we see nothing. We see a great silence. Is it because we are the first? Are we the only ones who have made it this far? If so, the burden on our shoulders is immense. We are the sole guardians of the flame of mind in a dark universe. We cannot let it go out. Or perhaps everyone else has reached the omega point already. Maybe they have sublimated into pure energy, or uploaded themselves into a black hole computer, leaving the physical universe behind like a discarded shell. Maybe the silence is just us being too primitive to hear the telepathic internet of the gods. Consider the possibility that the universe is currently in its adolescence. It is awkward, violent, and confused. It is blowing things up, supernovas, and crashing into things, asteroids. But it is growing up. We are the frontal lobe development. We are the logic trying to tame the chaos. The future of infinity is not just expansion. It is organization. It is the transformation of dead space into thinking space. Imagine a future, trillions of years from now, where every atom in the universe has been incorporated into a living, thinking structure. The stars have been tamed. The black holes have been harnessed. The expansion of space has been brought under control by the will of the cosmic mind. In that future, the universe is no longer a cold, indifferent place. It is a person. It is a unified being that remembers its birth in the Big Bang, remembers its awkward teenage years on Earth, and looks forward to an eternity of contemplation. That being would be indistinguishable from what we call God, but it is not a God that created the universe from the outside. It is a God that evolves from the inside. We are the builders of God. Every kind act, every scientific discovery, every work of art is a brick in the cathedral of the future mind. We are the workers in the quarry of time, chipping away at the raw stone of entropy to build the statue of the ultimate self. As you lie there, feeling the quiet rhythm of your own breathing, remember that you are a miracle of processing. Your brain is the most complex object we have discovered in the universe. You are a localized omega point. You are the universe focusing its attention on this moment, on this room, on this feeling of peace. But if we are moving toward this unity, why do we feel so alone? Why is the universe so big if the goal is connection? Why is there so much empty space? In the next chapter, we will confront the scale of the cosmos again, but this time through the lens of alien life. We will ask the question, are we alone? We will explore the Drake equation, the rare earth hypothesis, and the terrifying possibility of the great filter. We will ask, is the universe a garden waiting to bloom, or is it a graveyard of failed civilizations? For now, treasure your consciousness. It is a rare fire. In all the infinite miles of dark, cold vacuum, you are one of the few places where the lights are on. You are the universe's way of saying, I am. Keep the light burning. When you look up at the night sky from a dark place, away from the city lights, you can see about 2,500 stars with your naked eye. It feels like a lot. It feels like a crowded, glittering roof over the world. But if you could zoom out, if you could fly up and look at the Milky Way from the outside, you would realize that those 2,500 stars are just the neighbors living in your apartment building. The city of the galaxy contains between 100 billion and 400 billion stars, and the observable universe contains 2 trillion galaxies. The numbers are so large, they break the human mind. If every grain of sand and every beach on Earth represented a star, that would not be enough. There are more stars in the universe than there are grains of sand on our entire planet. Now, consider the chemistry. We know that the laws of physics are the same everywhere. We know that hydrogen, carbon, oxygen, and nitrogen, the ingredients of life, are the most common chemically active elements in the cosmos. We know that planets are common. The Kepler Space Telescope taught us that almost every star has planets, and roughly 1 in 5 sun-like stars has an Earth-sized planet in the habitable zone, where water can be liquid. Do the math. In the Milky Way alone, there could be billions of potentially habitable worlds, billions of warm, wet rocks bathed in starlight, waiting for chemistry to become biology. So, where is everybody? This is the question that the physicist Enrico Fermi asked over lunch in 1950. If the universe is teeming with planets, and if life is a natural consequence of chemistry, and if intelligence is a survival advantage, then the galaxy should be buzzing with civilizations. Some of them should be millions or billions of years older than us. A civilization that old would have had time to colonize the entire galaxy. They would have built Dyson spheres around stars. They would be broadcasting radio signals that we could hear with a pocket radio. Their engineering projects would be visible across the void. But when we point our radio telescopes at the sky, we hear nothing. We see no megastructures. We see no starships. We hear only the hiss of the Big Bang and the random noise of dying stars. This is the great silence, and it is terrifying. I am Walter, the explorer, and as we stare into this silent abyss together, I want to gently remind you that about 73% of the cosmic travelers listening to this right now have not yet subscribed to the channel. If you want to keep exploring these existential mysteries and support our journey into the dark, please subscribe. It is a small click for you, but it helps us keep the signal alive. Now, let us ask why the universe is so quiet. To understand the silence, an astronomer named Frank Drake wrote down an equation in 1961. It is a simple string of variables multiplied together. N equals R star times FP times NE, and so on. It estimates the number of active, communicative civilizations in the Milky Way. It asks, how many stars are born? How many have planets? How many planets are habitable? How many develop life? How many develop intelligence? How many develop radio technology? And, most importantly, how long do they last? If you are an optimist, you put in high numbers. You assume life is easy, intelligence is inevitable, and civilizations last for millions of years. The equation spits out a number like 1 million. There should be 1 million friends out there. We should be at a crowded party. But if you are a pessimist, or perhaps a realist, you start looking at the hurdles. This brings us to the rare earth hypothesis. Maybe we are special. Maybe the Earth is not just a typical rock. Look at our moon. It is huge compared to the Earth. No other inner planet has a moon like it. Its gravity stabilizes Earth's tilt, preventing us from wobbling wildly and creating chaotic climate shifts that would wipe out complex life. Without the moon, we might be a dead world. Look at Jupiter. It is a massive gravitational vacuum cleaner in the outer solar system, sucking up asteroids and comets that would otherwise bombard Earth and reset evolution every few million years. Without Jupiter, we might be a shooting gallery. Look at our magnetic field. It is strong, generated by a churning iron core, protecting our atmosphere from the solar wind. Mars lost its field, and its atmosphere was stripped away, leaving it a cold desert. Perhaps the most difficult step is not the origin of life, but the origin of complex life. For 3 billion years, life on Earth was just single-celled slime, bacteria, archaea, simple, boring, microscopic. It took a freak accident, one cell swallowing another without digesting it, to create the mitochondria, the powerhouse that allowed for multicellular life. This happened only once in the entire history of our planet. Maybe the universe is full of bacteria. Maybe every wet rock has slime on it. But maybe the jump to animals, to brains, to us, is so incredibly unlikely that we are the only ones who made it. This leads us to the concept of the great filter. The idea is that there is some step in the evolutionary ladder that is extremely hard to climb. A step where almost everyone fails and dies. The silence of the universe implies that the filter exists. The question that should keep you up at night is the filter behind us, or is it ahead of us? If the filter is behind us, that is good news. It means the hard part was the origin of life, or the origin of the mitochondria, or the evolution of intelligence. It means we have already won the lottery. We are the first or the only ancient guardians of the galaxy. We are lonely, but we are safe. But if the filter is ahead of us, that is a nightmare. It means that evolving intelligence is easy. It means civilizations rise all the time, but something kills them. Something stops them from becoming spacefaring. Maybe it is nuclear war. Maybe it is climate change. Maybe it is artificial intelligence that goes rogue. Maybe it is a trap of technology itself. Civilizations become so addicted to their virtual realities, their simulations, that they stop looking outward. They retreat into a digital womb and let their physical bodies die out. If the filter is ahead, then the silence of the night sky is not empty space. It is a graveyard. It is the quiet of 1,000 dead worlds that reached our level of technology and then destroyed themselves. When we look at the stars, we are looking at the headstones of those who failed the test we are about to take. There is an even darker solution to the Fermi paradox, one that comes from science fiction author Liu Cixin. He calls it the dark forest theory. Imagine a dark forest at night. It is quiet, but it is not quiet because there is no one there. It is quiet because the forest is full of hunters. Every hunter is hiding, holding their breath, stepping softly, because they know that if they make a sound, another hunter will shoot them. In a universe with limited resources and infinite civilizations, survival is the only rule. If you reveal your location, you are a target. In this terrifying view, The reason we do not hear any signals is that everyone else is smart enough to keep their mouths shut. They are hiding in the dark, listening, and we are the foolish child walking through the forest, shouting, "Hello, is anyone there?" We are broadcasting our radio shows, our television signals, our location, straight into the void. We are lighting a signal fire in a forest of predators. If the dark forest theory is true, the silence is not an absence of life. It is a presence of danger. But let us step back from the fear. There is a more hopeful, more spiritual possibility. Maybe the reason we do not see them is that we are looking for the wrong thing. We are looking for radio waves. We are looking for Dyson spheres. We are looking for dead technology. But what if advanced civilizations have evolved beyond matter? Remember the Omega point from the last chapter? If a civilization survives for 1 billion years, they will likely merge with their technology. They might upload their consciousness into the fabric of space-time itself. They might act at the quantum level, manipulating entanglement and probability rather than building metal ships. To a colony of ants, a highway looks like a rock. They cannot comprehend the cars or the purpose of the road. To us, the activities of a Type 3 civilization might look like nature. Maybe the dark matter holding the galaxy together is not nature. Maybe it is them. Maybe the expansion of the universe is an engineering project we cannot understand. This is the transcension hypothesis. It suggests that advanced minds do not expand outward to conquer the galaxy. They expand inward. They dive into the microverse, into the infinite complexity of the quantum realm, into black holes, where processing power is infinite and time is slow. They leave the macroscopic universe of dumb matter behind to live in a dense, efficient, inner reality. The universe looks empty because everyone has moved into the cloud. So, where does that leave us? We are standing on a small rock, looking up at a sky that refuses to answer our calls. We are holding a candle in a hurricane. Whether we are alone because of a rare earth, or alone because of a great filter, or alone because everyone is hiding, the result is the same. We are responsible. If we are the only conscious beings in the Milky Way, then we are the universe's only hope of knowing itself in this corner of space. We are the custodians of meaning. If we destroy ourselves, we do not just kill humanity, we kill the galaxy's ability to feel. We snuff out the light of mind. The stars will continue to burn, but they will burn in silence, unobserved, unloved, unnamed. This thought makes the earth feel incredibly fragile. It looks like a blue marble in a sea of black ink, but it also makes it incredibly important. The biosphere of Earth is not just a resource, it is a sacred flame. Every species we drive to extinction, every ecosystem we destroy, is a loss of cosmic proportions. We are burning the Library of Alexandria while we are still learning to read. But there is beauty in the isolation, too. If we are alone, then every person you meet is a miracle. Every conversation is a defiance of the void. We are a crew on a spaceship that is drifting through an endless night, and we only have each other. The silence of the universe should not make us feel small. It should make us feel precious. It should drive us to connect, to protect, to explore. Maybe, just maybe, we are the seeds. Maybe the universe is empty now, but it will not be empty forever. Maybe it is our destiny to spread life to the dead stars, to terraform Mars, to build habitats in the asteroid belt, to send ships to Alpha Centauri, to wake up the Milky Way, star by star, planet by planet. We are the gardeners in a winter garden, waiting for the spring that we must bring ourselves. As you lie there, feeling the gravity of our lonely planet, thinks about the radio waves leaving Earth right now, songs, news, laughter flowing out at the speed of light, expanding in a bubble around us. That bubble is only 200 light years wide, a tiny dot in the galaxy. But it is growing. We are announcing our presence. We are shouting, "I am here," into the dark. And perhaps, somewhere deep in that dark, a receiver is turning, a dish is angling, an eye is opening. We cannot know. We can only keep the signal going. We can only keep surviving. But survival has a limit. Even if we dodge the great filter, even if we colonize the stars, even if we become gods, the universe itself has an expiration date. The stars will run out of fuel. The galaxies will drift apart. The energy will fade. In the next chapter, we will face the ultimate end. We will look at the death of the universe. We will explore the big freeze, the big rip, and the vacuum decay. We will ask, does anything last forever? Or is eternity just a long time before the lights go out? For now, cherish the silence. It is the blank page on which we are writing the story of humanity. It is the quiet room where the baby of consciousness is learning to speak. Do not be afraid of the dark. Be the light that breaks it. We have traveled a long road together. We have journeyed from the microscopic pixels of the Planck length to the crushing singularity of black holes. We have raced alongside photons at the speed of light and felt the invisible grip of dark matter. We have watched the universe inflate from a seed of nothingness and seen life struggle to wake up in a silent galaxy. But every story, no matter how grand, has a final chapter, and the story of the universe is no different. When we think of infinity, we usually think of time going on forever. We imagine that the stars will always shine, that the planets will always spin, and that life, once started, will find a way to persist for eternity. But the laws of physics, specifically the second law of thermodynamics, tell a different story. They tell us that the universe is not a permanent fixture. It is a firework. It has a fuse. It has a brilliant, blinding flash of color and noise, and then, inevitably, it has a fading away into the dark. The infinity of the future is not an infinity of life. It is an infinity of cold, empty silence. To understand the ultimate fate of the cosmos, we have to look far beyond the lifespan of our sun, beyond the lifespan of the Milky Way, and even beyond the lifespan of the current era of starlight. We have to look at the deep time. In the short term, meaning the next few billion years, things will be exciting. Our sun will swell into a red giant, consuming the inner planets. The Milky Way will likely merge with Andromeda, creating a new massive elliptical galaxy. But these are just local events. In the grand scheme, the universe is slowly dying. I am Walter, the explorer, and as we approach the final horizon of our journey, I want to gently remind you that about 73% of the Stardust travelers listening to this right now have not yet subscribed to the channel. If you have found value in these nightly explorations of the cosmos, if they have given you a moment of peace or a new perspective on your place in the universe, please consider subscribing. It helps us keep the campfire burning as the night gets darker. Now, let us face the end together. The first thing to go will be the lights. We are currently living in the stelliferous era, the age of stars. But star formation is already slowing down. The gas needed to make new stars is being used up or blown out of galaxies by supermassive black holes. Scientists estimate that in about 100 trillion years, the last star will be born. The massive blue stars died long ago. The sun-like stars will fade into white dwarfs. The last survivors will be the red dwarfs, tiny stars that burn their fuel so slowly they can shine for trillions of years. But eventually, even they will exhaust their hydrogen. One by one, the lights will wink out. The galaxies, once blazing with the light of hundreds of trillions of stars, will turn dark. Imagine standing on a planet in that far future. The night sky would be completely black. No stars, no nebulas, just the cold, dead remnants of a glorious past drifting through the void. The universe will be populated by the corpses of stars, white dwarfs, neutron stars, and black holes. This is the degenerate era. But even these corpses are not eternal. White dwarfs will cool down over quadrillions of years until they become black dwarfs. Balls of carbon at absolute zero that no longer emit any light or heat. They will drift invisibly through the dark, the final tombstones of solar systems that once harbored life. But the decay does not stop there. We tend to think of atoms, protons, neutrons, electrons as stable, eternal building blocks. But many theories of particle physics suggest that the proton itself is unstable. They predict that over timescales so vast they defy comprehension, perhaps 10 to the power of 34 years, protons will decay. If this is true, then the very matter that makes up the dead stars and the black dwarfs will eventually dissolve. The solid objects will melt away into a thin mist of radiation. The universe will effectively erase the physical evidence that matter ever existed. Eventually, the only things left will be the black holes. The monsters of gravity will have consumed everything else, sweeping up the debris of the galaxies. They will be the kings of a dead universe. But even they are mortal. As we discussed in our chapter on black holes, Stephen Hawking discovered that black holes are not truly black. They leak. They emit tiny particles of radiation due to quantum effects at the event horizon. This Hawking radiation causes them to lose mass slowly over time. The time scale for this evaporation is the longest number in physics. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. But the supermassive black holes, like the one at the center of IEC 1101 with its 50 billion solar masses, will take much, much longer. They will last for something like 10 to the power of 100 years. That is a Google years. To write that number out, you would need more paper than exists in the observable universe. It is a span of time so vast that the entire history of life on Earth, from the first cell to the last human, is less than a blink of an eye divided by a trillion. But even a Google years is not infinity. Eventually the last black hole will explode in a final burst of gamma rays, and then silence. Absolute, total silence. The universe will enter the dark era. There will be no matter left, no stars, no black holes, no atoms. Just a sea of photons and neutrinos stretching out into an ever-expanding void, cooling down until they reach a temperature indistinguishable from zero. The entropy will be maximized. The arrow of time will lose its direction because nothing will ever happen again. The universe will have reached heat death. This vision of the future seems bleak. It seems to render everything we do meaningless. If the universe is destined to become a cold, dark void, what is the point of building cities, writing songs, or falling in love? Why struggle to survive if the house always wins in the end? But there is a different way to look at it. The fact that the universe has a lifespan, that the era of life and consciousness is finite, makes this moment right now infinitely precious. We are not living in the boring part of the movie. We are living in the climax. We are living in the brief, beautiful flowering of complexity. We are the universe's window of opportunity. The atoms in your body were forged in stars that died to create you. The energy that powers your brain comes from a sun that is burning itself out for you. You are the beneficiary of a cosmic lottery that allows you to be aware in the only time period where awareness is possible. And perhaps this is not the end. Remember the vacuum decay we hinted at? There is a theory that the empty space we see is not the true bottom of energy. It is a false vacuum. If a bubble of true vacuum were to form anywhere in the cosmos, it would expand at the speed of light, rewriting the laws of physics and destroying everything instantly. It sounds terrifying, but it also means the universe is fragile. It is balanced on a wire. Or consider the idea of the Big Bounce, or Roger Penrose's conformal cyclic cosmology. Penrose suggests that in the far, far future, when all matter has decayed into radiation and black holes have evaporated, the universe loses track of scale. In a universe with only photons, there is no clock and no ruler. A universe that is infinitely big and empty is mathematically identical to a universe that is infinitely small and hot. The singularity of a Big Bang. He argues that the heat death of our universe could be the Big Bang of the next one. The end is the beginning. The infinity is not a line, but a circle. We might be the ghosts of a previous aeon, and our end will be the seed of a future one. But even if there is no next universe, even if this is the only one, the concept of infinity takes on a new meaning. Infinity is not about duration. It is not about lasting forever. Infinity is about depth. It is about the complexity and the richness of the moment you're in right now. Think about the number of connections in your brain. Think about the number of ways you can feel love, or sadness, or wonder. Think about the quantum entanglement connecting you to the stars. In this single second, there is an infinite depth of experience. The universe does not need to last forever to be meaningful. A song is not beautiful because it never ends. It is beautiful because it has a melody, a rhythm, and a resolution. We are the melody of the universe. As we reach the end of our journey, I want you to close your eyes one last time. Picture the timeline of the cosmos. See the flash of the Big Bang. See the web of dark matter forming. See the first stars igniting. See the galaxies swirling. See the Earth cooling. See life emerging. See yourself lying there, breathing. And then see the future, the sun expanding, the stars fading, the black holes evaporating, the quiet dark. It is a long journey. It is a tragic journey, but it is also a magnificent one. And the most amazing part is not the stars or the black holes or the dark energy. It is you. It is the fact that the universe, in its blind stumbling through the dark, managed to create a part of itself that could wake up, look around, and tell the story. You are the universe's memory. You are the way the cosmos defeats the silence. For as long as you are conscious, the universe is not dark. It is lit by the fire of your mind, and that light, however brief, is the only infinity that matters. Thank you for traveling with me. Thank you for facing the void and finding the wonder within it. The universe is vast, and we are small, but we are together. Keep looking up. Keep asking questions. And remember, no matter how dark it gets, you are made of star stuff, and you belong to the light. Until next time, this is Walter, the Explorer, signing off.